Okay, everyone. Well, good morning and welcome to round one of the competition for the International Mission to Mars Design Challenge. The first team that's going to go today is our Asia team. And so I believe, Carl, you're going to go ahead and present.
Which number team is that?
This is number two, team two. I'm going to go ahead and start the timer. You guys have 30 minutes. Go ahead and get started.
Good day, everyone. I am Carl Odrin. This is Team New Era hailing from India, Singapore, the USA, and the Philippines. New Era is also the name of our 1.5-year mission, and it comes from the acronym describing the different components of our project. We have the name Nourish for the greenhouse, Endure for the habitat, and Wonder spacesuits. There's also the Explore Rover, the balloon named Reach, and the truck named Achieve. As much as we need this set of equipment, the qualities associated with their names will also play a deep role in pioneering a humans to Mars mission. Without further ado, the New Era is divided into three main objectives: life on Mars, atmosphere and weather, and human sustainability. Under life on Mars, we plan to experiment with hydroponics using in situ resources and search for signs of life in areas nearby ice. Under atmosphere and weather, we're interested in how lightning events or dust devils might be involved in the peculiar distribution of methane on Mars. And under human sustainability, we're aiming to support humans in terms of food, power, and long-term residence. Utopia Planitia was chosen as a landing site for its alignment with the mission objectives. Aside from being suitable for landing because it has a low elevation, Utopia Planitia spans 3,300 kilometers of intriguing textures and ice-related geologic formations. The brain terrain, for instance, has ridges consisting of an ice core, which can be a water source. The Mars Reconnaissance has also confirmed ice at the surface or right below it, making its extraction much easier. In terms of geology and in situ resource utilization, Utopia Planetia's potential is immense. According to Sikorsky, it features volcanoes, ancient lava pools, river channels, and the like. These are promising areas for life and can be examined with our autonomous Explorer rover. On the soil, Viking 1 has detected minerals that can be utilized for growing plants on Mars, not to mention the nitrogen and significant amounts of carbon dioxide found in the atmosphere. In addition, Utopia Planetia's crater will only be 45 kilometers away from Amazonis Planitia, a convenient distance for the rover. The proximity of Amazonis makes Utopia a good landing site because the unusual presence of methane on Amazonis and its high frequency of dust devils bring us to another objective, which is studying the atmosphere and weather. In 2003, a team at NASA Goddard found trace amounts of methane on Mars. In 2014, Curiosity found stranger results. There had been a tenfold increase in atmospheric methane, averaging 7 parts per billion. The problem is we don't know where the methane is coming from, considering there are no confirmed methanogens that exist on Mars. Of course, there could be non-biological processes like water-rock reactions, and an interesting hypothesis is that dust devils might be involved in distributing methane. Because particles in dust devils are rubbing against each other, small lightning discharges can trigger the production of hydrogen peroxide, which reacts with methane. This gives an answer to why some areas of Mars have lower levels of methane and some have higher ones. If we prove that hydrogen peroxide is breaking down Martian methane, then we have more reason to believe that there once have been higher levels of methane than expected. This points back to a stronger possibility of methanogens once again. This experiment has no caveat. If the balloon's hypothesis were found to be null, then the rover that Rebuttals will talk about later will have more reason to do geologic research for signs of methane on the soil. So, Team New Era proposes a two-part experiment, one with the balloon monitoring from above and one with the rover examining the dust and rocks underground. The balloons must fly around 10 kilometers high to keep a safe yet close distance from the dust devils. Taking reference from the Mars aerial platform, the Reach balloon will circumnavigate Mars 20 to 50 times. In 1.5 years, the data collected will provide a vast wealth of information about the planet's atmosphere. In case the balloon crashes, the substitute stored in the Hab will be deployed by a Marsonaut plus a mechanic. The balloon must be inflated slowly at first to prevent damaging the balloon fabric, and then faster until the balloon reaches a diameter of 4.1 meters. The buoyancy force equation gives this diameter as the mass of the fabric has to be 5.4 kilograms. Aside from the basic atmospheric monitors for temperature, pressure, etc., the hypercam methane will be the main instrument to detect methane. As a non-invasive spectrometer, the hypercam methane can maintain a wide range of detection, even for compounds in low concentrations. From a balloon, it can visualize methane in real time and localize the source and direction of the gas. This will provide new data on its mysterious distributions on Mars. I have mentioned earlier how lightning events might be destroying methane, so the balloon will also have a microwave detector for electrical discharges. This is called the Agile digital detector. The University of Michigan has already developed such a microwave detector, which can distinguish natural emission signals from near interference. For better precision, the instrument will be paired with the kurtosis detector, which is already in use on Earth-based observatories. The kurtosis detector processes signals by differentiating thermal from non-thermal radiation, allowing it to pinpoint the cell lightning events. Bringing one of them on Mars will give atmospheric scientists a front-seat view of smaller-scale lightning events that might be invisible to Earth-based instruments. That's it for the balloon, and Dibha will talk about the rover next.
So for the Explore part of our New Era mission, we're going to be focusing on the geology and the search for life on Mars using our specialized rover. So we're going to be using ice for various things on our mission, as you can see in this mission plan here. So we want to actually use the presence of ice to look for life as well. Now, if we're looking for life, we of course need to be prepared for the scenario that we actually find it and what we're going to do at that point. Well, we've designed our mission in a way that we're not actually completely dependent on water for our food or our oxygen production, our energy production. We do have other sources. So if life is found inside the ice on Mars, we can temporarily stop all of our operations for at least a month, and we will be able to return back to Earth Mission Control to figure out what our next steps are. There's really no consensus on what we can do for life on Mars, so we're hoping that Earth Mission Control can help us figure things out as we go along in the scenario that we do find life. If we do not find life on Mars, we're going to continue with our normal plan of using the ice on Mars for liquid water production, oxygen production, methane production for energy, and to heat our habitation. So that whole process starts off with our rover over here, the Mars Exploration and Reconnaissance Rover, or MER. So this rover is especially designed to go out into places where it's remotely controlled by the crew inside the habitation, and it's able to drill into the ground to not only look for ice and do geologic research and sample collection, but also be able to return all those things back to the crew so they can do further testing inside the Hab itself. So the first main part of this rover sort of builds on the methane camera that we were looking at before. This methane detection system is going to be attached to the bottom back of the rover, and it's going to dig into the ground using laser and look for signs of methane deposits. This is going to be basically secondary to the other detection systems, so it's supplementary, and the GAMAS that's attached to the TLS, the tunable laser spectrometer, and the gas and scattering media absorption spectroscopy, these are both going to work together to make sure dust devils do not actually affect the detection systems. The next important part of this rover is the 3 life detection systems and 3 forms of communication with the habitation. So the first main, most important form of life detection is the solid, the sign of life detector. This uses 2 main parts, the sandwich microwave immunocy and the competitive microwave immunocy, to look for life that is very similar to that on Earth. So proteins, EPS, nucleic acid, whole cells, and those types of things are the things that the solid works in detecting. If this comes back positive, our astronauts immediately know the sort of life that they're dealing with, and this gives them a lot of information to update mission control. The second important thing that we have is called the microfluidic life analyzer. This is designed to test for, like it says, 512 different biological compounds, and based on what compounds are present, the crew and the mission control on Earth can extrapolate not only how those compounds got there, but also, what might have produced them in the first place. And if our crew needs even more information on top of that, we have a mass spectrometer, the mini being referring to the size of the spectrometer on the back of the rover. And this will help us analyze all of the chemical makeup of whatever sample we're taking so we can get a better idea of the environment that any of these organic compounds were produced in. The 3 main forms of communication are the low gain, high gain, and ultra high frequency antennas. These allow the rover to communicate directly to the Hab through orbiters, through direct radio control, and even back all the way to Earth mission control if really needed. So this allows us to have easy communication with the rover and make sure we do not lose it on the surface of Mars. So the next important part about this whole system is, of course, how we're getting our samples out of the ground. So we have allowed our rover to carry up to 50 pounds of samples as part of moving around and stuff. We want our crew to be able to collect as many samples as they feel is necessary from any certain area. The way we're going to be collecting our samples is that 1 meter long drill auger that you see on the bottom right of the screen there. The The auger here is specially designed to be rotary percussive, which means if the rock is very hard on Mars, we can sort of just tap it like a hammer and it'll crack everything and we can continue drilling normally. We also have a special design for the rotary parts of the drill itself, so it can dig into the ground very easily and not get stuck. That's the absolute last thing that we want. This drill is going to be controlled remotely, just like the rest of the rover is, by the crew, but this drill is relatively smart itself. It's designed in a special way to take data from the bit that we're going to look at in a second to make sure it doesn't get stuck in the ice on Mars by drilling too quickly and getting the end stuck in the ground. We're going to be using a process called biting, so we're going to go down a little, come back up, down a little, come back up to make sure that not only our rover doesn't get stuck, but another reason I'll share in a second. We're going to be using a pneumatic tube system to bring all of our samples from the front of the rover to the back, just because this is the way to make sure that we contaminate everything at least. The last important parts of this rover are the bit sensor and the tire. I'll start with the bit as well, just to start off. So the bit sensor is very important because the temperature sensor inside of it is very useful for geologists because we don't actually know much about the subsurface temperatures on Mars. So by doing the process of biting, we're able to look into the ground and say like, hey, this is the temperature of this depth, this is the temperature of that depth, so on and so forth, which can be useful for a geologist. The next important thing is the electrodes. You can actually find the solubility level of all the ice on Mars, and this will be very useful for figuring out not only the environment that it was in before, but to make sure that when we're drilling with our big drill later to get all this ice and stuff out of the ground, assuming we don't find life, we can drill at the highest, most efficient speed possible. So the last main thing about this whole rover is the spring tires that it has. Spring tires have not been used on Mars yet, but they're actually very, very important to our mission because, as you can see in that bottom picture there, they are bendable and they go back into shape that they originally were. So this allows us to roll over things like jagged rocks. It allows us to go into canyons and stuff and not worry about getting our rover stuck in there. And this will make our robot not only more efficient, but less likely to break down. Now, Brian is going to continue by talking about what we're going to do with the ice exactly once we figure out it has no life.
I am Brian Reichert, and it was my responsibility to design the manned Mars vehicle, Achieve. This vehicle was designed to provide a modular platform to assist the crew with either exploration and scientific research or drilling for ice, a mission-critical component. The portable habitation module is a removable section from the Achieve rover and can allow longer-term exploration and study of the Martian landscape. Having a small laboratory and small airlock to allow safe transfer of samples into the Hab to assist with easier geological analysis. It also boasts some small bunks to allow the crew to live overnight in the cabin to allow longer journeys of scientific research. The drilling module utilizes a large 16-foot, about 5-meter long tungsten carbide drill bit, similar design and concept to hand drills used by ice fishermen connected to a larger trackable crane to allow mobility to provide the 420 gallons, roughly 1,590 liters of water to supply the crew on a weekly basis. After the ice has been drilled from the ground, the ice is melted and filtered through an evaporator filter, as it reliably separates water from possible unknown contaminants in the water. Should the water be used by either the hydroponics system or consumed by the crew, the water will be placed in a special electrolysis chamber that utilizes a centrifuge to increase efficiency. The resulting products will be separated naturally by the reaction and utilized for either life support, methane production, or methane combustion. The hydrogen product by electrolysis will be reacted with CO2 taken directly from the atmosphere at a pressure of 3 Earth atmospheres and around 400 degrees Celsius to produce methane, which will be used for both heating and powering the main habitat. Heating will be conducted as the products from combustion of methane from a generator are flowed between the layers of the habitat and flowed through the greenhouse to supply ample CO2 to the plants being grown in the hydroponic system. Should the heating be too excessive for the crew can vent the heated steam and CO2 to cool down the Hab without worry of depressurization, as the ventilation and heating system are airtight and scaled and sealed from the rest of the Hab.
Hi everyone, I'm Lexi and I'm going to be talking about the habitat and disposal planning for our mission. So here we can see a 3D model of the habitat, and it shows it's a modular structure with different modules surrounding the central living module right over here. Here is the ground layer of the habitat, and the total area of the hab is 2,000 square feet, which is about 183.65 meters square, and this has enough space for repairing equipment such as robots. The superstructures of the habitat and the nourish greenhouses will be 3D printed by robotic 3D printers that will be sent to the surface in a cargo capsule before the crew's arrival. And this will use Martian regolith, as this is ultra-protect from solar and cosmic radiation. Below the regolith layer, there will be an inflatable layer made from high-density polyethylene or HDPE, as this is lightweight, weather-resistant, and durable. Trash mist made from disinfected feces may also be used as an extra layer of protection between the regolith and the inflatable. Here I've just correlated an icon to each module of the hab. Here we can see how the different modules are arranged around the central living module, and between the some of the modules and the central living module, there are airlocks to allow for separation of the different modules and save energy, as in some of the modules 24/7 air and temperature regulation is not needed, so this can be turned off and on when needed, and hence save energy. The total energy requirement, the total daily energy requirement for the hab is between 75 kilowatts and 90 kilowatts. Now it's disposal planning. So for the toilets on Mars, the toilet will be built on Mars and will be self-cleaning toilets made from metallic materials such as titanium. And these toilets will resemble the universal waste management system that NASA currently has. And the vacuumability of these toilets will ensure minimal use of water and help in the segregation of urine and feces. Then a reactor called the heat melt compactor, will process this waste. In addition, during their EVAs, astronauts will wear maximum absorbency garments, which will be much more comfortable than catheters or bladder bags in the past. And currently, these are disposable solutions. However, biodegradable ones may be also within the next 10 years. For packaging, it will take up about 1 ton of the weight, and for machinery, it is unavoidable that we use plastic packaging, but for other items such as food or any other matter, we may be able to use lightweight materials such as bamboo, cornstarch, or mycelium to make biodegradable packaging. For clothing, as the crew is staying on Mars for 18 months, it would be optimal that they wear their clothes for the maximum possible time, but we do have a cleaning system in place, which is dry cleaning with liquid carbon dioxide, as that does not use any water and is non-toxic and non-flammable. And we also will have a system in place to reuse spare parts from irreparably damaged equipment or items, such as the shield of a rover for germinating plants, or other useful materials from broken down devices. Of course, we will always have contingencies and backup systems so that the astronauts are not stranded without an important system. Thank you.
Hello everyone, my name is Venkata, and I will be talking about heating, communication, and various aspects of the Wonder spacesuits. So heating on the Martian surface is very important because the Martian surface is much colder than Earth. Temperatures can get down to negative 125 degrees Celsius. So the Martianauts will need a thermal regulating system. And this system will be very similar to the active thermal control system on the ISS, and this will be used in the HAB. There will be 3 subsystems. These will be the heat collection, transportation, and rejection systems. Heating in the HAB will be supported by steam given off from the production of methane during the Sabatier reaction. And this steam, when there's excess, it will be transported to the greenhouse, and then that heat will be given to the greenhouse through radiators there. Heat will be transported through pathways in the HAB. Communication is also very important on Mars. Crew will use built-in ham radios in the spacesuit during truck excursions. Beacons for radios will be placed in the truck and the HAB. The truck will have a portable beacon, and the HAB will have a permanent one. The radius for each beacon is around 150 to 200 meters. Small foldable cell phones with terabyte delivery, infrared delivery, will be present in all spacesuits in case of emergency. And Seabird is basically a direct communication link to Earth using lasers. And also a high-gain antenna using Mars Endeavour will be used to contact Earth. Next we have the one-day spacesuits. So our primary goal is preventing contamination of Mars life, since our biggest goal for the New Era mission is looking for life on Mars. We also want to use research in the environment and provide greater dexterity and comfort for the astronauts, so we can do longer EVAs or extravehicular activities. So the innermost layer will be tricoat layer for the Marsonaut skin. After that, there will be various memory alloys to provide support to the suits. After that is a Dacron layer. Between the Dacron and Mylar layers, there'll be various nylon layers, one of which will be neoprene, so that will provide flexibility to the suits in various temperatures. And then the outermost layer will be orthofabric with blue Maya coating. And blue Maya coating stands out very well in the Martian environment. All right, so the biggest design part we have here is that the outer part of the suit will be gas pressurized, and the inner part will be mechanical counter-pressurized, which basically means it'll have skin-tight elastic garments that hug the body and provide pressure that way instead of through gas. So this means that the suit is safer through redundancy, it allows more dexterity, and if you have an MCP layer, it'll be less weight than a traditional gas pressurized suit. The lower part will be pressurized by the MCP layer along with gas pressurized, and the GP part will come from the Martian atmosphere instead of oxygen from the life support system as previous space suit designs had it. This way less oxygen needs to be stored, and we're also using resources in the environment. The helmet and the upper torso will be separated by a neck dam, and the pressure in the helmet will also be slightly greater than the upper torso so that no carbon dioxide leaks up. And the expected weight will be 217.75 pounds. All right, now I'll hand it off to Arya to talk about the greenhouse and food.
Arya from New Era, and I'm going to be talking about food and water sustainability on Mars. So the system of growing food that we have decided on is hydroponics, and I'm going to make my case by stating why we shouldn't be using the other systems of growing food, that is aquaponics and aeroponics. So aquaponics, although advantageous, is extremely unreliable, especially with regard to the first manned mission to Mars. And the thing with aquaponics is that if something were to happen to the fish that are included in aquaponics, then the entire ecosystem is gone for a toss, and at the end of the day, it just isn't a very reliable source. And the maintenance of this entire ecosystem requires a lot of work. And in the case of aeroponics, if something were to happen to the plants, then the plants will die immediately. If the nutrient supply of the plants was somehow damaged, then yes, they will die immediately. And although hydroponics will also die within a short span of time, they will die significantly a lot longer than the aeroponic system, the plants grown by aeroponics, and hence hydroponics in this case is the most efficient system to be growing plants on Mars. So there are two greenhouses in number for safety purposes. If something were to happen to one greenhouse, then we have the other greenhouse, and we will be fixing the first greenhouse while relying on the second one for our source of food. We have the greenhouse is 3D printed, not the greenhouse itself, but it is protected by a 3D printed cover, and inside we have an inflatable, which is the greenhouse itself, and that is where the plants are going to be grown hydroponically. And the plants are supplied with artificial light inside the greenhouse. There is shared air between the greenhouse and the Hab, and initially when the plants are growing, they will be supplied with CO2 from the outside atmosphere of Mars, and then the lock will be opened between the greenhouse and the Hab, which is when the air will be shared, and the crew members can benefit from the oxygen that is released by the food. So the food that we're bringing includes potatoes, sweet potatoes, carrots, lentils, tomatoes, spinach, soybeans, and rocket leaves, and these are arranged in descending order based on how long they take to grow. And these crops also be grown depending on the same parameters. So these crops will be rotated based on the same parameters. So every 8 weeks, the potatoes will be replanted and harvested. Will be harvested and replanted, and the same goes for all of the other crops as well. So these were chosen on the basis of the nutrients that the crew will be requiring, and this is enough for the crew to sustain for a long period of time with these said nutrients. We also decided to go with mushrooms as well, and the mushroom tissue is going to be brought to Mars along with the food that comes to Mars. So the mycelium of the mushroom will be grown in the lab, and it's kept with some extra seeds brought to Mars, which will then be transported or kept or relocated into compost blocks, which is where the mushrooms will be grown. And this compost box or multiple compost boxes would include human feces as well as the remaining plant parts that we do not eat. And the mushroom growing there will be rich in protein and potassium, which is highly beneficial to the crew members. So the waste management and water cycle is fairly simple. We have the urine as well as the feces. So the urine could go one of two ways. It could go into a urine processor, which is where it will be separated into urea and water. The urea could be used as a fertilizer in the hydroponic system, and the water could be used for consumption as a last resort, or could be put into the water system of the hydroponic system, or the urine could just directly be put into the hydroponic system for it to go along with the water flow that exists inside the hydroponic system. The feces could be gone into a heat melt compactor, which is where it will be disinfected and dried, and it could be used as a fertilizer for the plants or as food as a last resort. Or the feces could be transported into a composting box, which is where it will grow along with, which is where the mushrooms will grow along with the remaining plant parts and the feces. Thank you.
Hi, I'm Maya, and I'm going to speak to you about our new era crew. Firstly, we have the selection process, which looks something like this. The fourth round will have 10 shortlisted candidates, out of which the 5 that will make the crew will be chosen based on their abilities to work as a team. The crew will be selected based on an age range, height range, as well as their experience and qualifications, and will be chosen in a manner that is representative and diverse. The crew should ideally consist of people that are psychologists, doctors, engineers, climatologists, and chemists to maximize the work that the crew can do on Mars. The training should include mechanical skills, training in AI and sample testing, as well as establishing ways of addressing conflicts within the team. The crew's physical health will be highly impacted due to the lack of fresh food and high amounts of radiation on Mars, and the impact of this can only be reduced by the dietary conditioning that the crew has, as well as be consistent with their calorie and water intake every day. A crew member's day should consist of about 2 hours of physical exercise every day. The mental health effects that the crew is going to face will include decline in brain function, development of sleep disorders, and increased conflicts with each other. The impact of this can be reduced by maintaining a personal log, spending some alone time, and performing breathing practices every day. The crew will have access to an SOS medical website in case of any advice or the immediate help that they need. Testing will include lactate testing, fluid shift testing, urine and blood testing, and ultrasounds. And the monitoring watch and strip will be on each crew member at all times to monitor their vital parameters. Each crew member will have access to a first aid kit, and medicine storage will be in the medical module. A crew member's day will look something like this, with crew time and work time, with sleep time and work time being about equal. Physical exercise and mental exercise will consist about 3 to 4 hours of their day, and the rest should be recuperation time. A crew member should ideally adapt habits like taking their waking heart rate that will help them as well as people on Earth to understand how their body is recovering. The daily water intake should be around 2.5 liters, while daily calorie intake should be around 3,000 calories. The crew should ideally schedule movie watching time or music listening time together to maintain the team environment, and perform urine and blood testing and Hab swabbing at least once in 2 weeks. Ideally, the crew should still perform 10 to 12 hours of astronaut training to help them keep in touch with mission objectives on such a long mission. Cleaning days should move on a rotatory basis through the month, with each astronaut being in charge of one of the days. And this is what the 18-month schedule for the new era crew looks like, with rover activity and drill and balloon research being spread over the overall months, while the initial months consist of setting up the central and facility modules. This is a summary of the total mass, cost, and power requirements that the mission needs, which includes the habitat, the greenhouse, the manned truck, as well as the spacesuits and subaterial reactor. Future research could possibly include in-depth work on aquaponics, on converting the mechanical energy of the crew to electrical energy, as well as bringing smaller mammals from Earth to test the reduced effects of gravity, and on reproductive health. Also, the research done by the Reach balloon and the Explore rover on this mission will prove important to future missions when looking for a landing site or a base site. Going to Mars will also prove insightful for human life on Earth as to how we can maximize, protect, and appreciate our resources. Exploration to Mars and beyond is a mixture of challenge and freedom that will hopefully influence people to discover entirely new definitions of citizen rights and new ways of organizing society. We are in the front seat for a new era of both science and society. Thank you.
All right, I think that is our entire presentation. I don't think we have time for questions, so thank you for all your attention.
Thank you so much, Team 2. That was fantastic. Okay, next up is Team 1, which is our Europe and Middle East team. So who would like to present?
Hi, so this is Leonard from my dad's computer. And so I'm a member of Team 1. Many of our teammates are in a camp and are not available right now, but we prepared a video to show you all, or a presentation with audio. I'll share that right now.
All right, you have 30 minutes.
Welcome to the presentation of Team 1. We are from Poland and the United Arab Emirates. Let's start.
Mars is full of interesting places, some of which present more advantages than the others. However, we decided to locate the first manned Mars base in a truly unique location, in Valles Marineris. The greatest canyon of the whole solar system provides such a vast amount of versatile scientific opportunities than no other place on the red planet. The exact location of
We lost the sound, Leonard.
and valleys, but probably the most important is water, which is proven to be abundant in Kandor-Kazma. It exists either as a vapor in the foggy air or is ready to be extracted from hydrated minerals. Speaking of minerals, Kandor-Kazma has rich deposits of sulfates and hematites. They are not only traces of the past conditions of the planet, but can also provide necessary materials for building or the production of fertilizers. Kandor-Kazma offers even more than water sources, a unique microclimate, and accessible mining sites. Its cliffs and slopes are the only places of Mars showing explicitly the geological past of the planet. This geological map, combined with the study of the samples from various log layers, will be our Rosette Stone for studying past Martian climate and the history of Valles Marineris itself. Finally, because our base is located at the equator, we will be exposed to much milder temperature conditions. The equatorial location also means a generally higher solar cell efficiency and greater fuel saving when landing or starting the rocket.
Carrying out research is the most important part of our mission. Living on Mars and surviving in our base is an experiment itself. We have to maximize our possibilities and conduct as much research to reach the limit of radiation exposure. That's why we want to give orders for robots and drones to gather samples from spots far away from our base. Scientists will be working on samples in our base camp laboratory and gather lots of samples to carry on Earth.
As we already managed to outline, there's a score of experiments waiting for our crew to conduct. Gathering samples of rocks using our 3D devices like laser or plasma drilling, compressed carbon dioxide, and energy supplies by SOFC will allow us to search for underground water sources, such as glaciers, or even traces of life. The latter has to be searched for rather deep, since the surface is sterilized by radiation. The experiments will require special equipment. For example, we'll use explosives produced on Mars and multifunctional seismic sensors to locate the best investigated sites. Another significant scientific goal is research on geology. Valles Marineris offers a wide range of materials from different periods of times in Mars history. Working with samples will let us to discover the processes that led to the formation of the canyon and whether water had anything to do with it. Scientists will also research the geological cross-section, expecting to find out more about volcanic activity of the planet.
So for this part, the audio corrupted, so I'll be explaining a bit. Oh, sorry. So our campaign for geology was to find life in water, and
We'll focus our attention on the physical properties and chemical composition of sampled minerals to determine the past conditions on the red planet. It is possible that they may also be used as tracers for long-gone Martian life. Another research will involve structures inside the canyon, especially shapes that resemble erosional features, like channels. We'll also try to reveal the mystery of recurring greenland slopes. We are determined to define if the water is a reason for the occurrence or not. We even expect to find lava tubes nearby Valles Marineris. As we study present condition in Valles Marineris, we will focus also on its unique microclimate. This covers monitoring its humidity, water vapor saturation, winds, temperature, pressure, and condensation. In most cases, we use our multifunctional automatic stations. Our team planned that the crew will test local sources to get materials necessary for building parts of the base and replacement parts for our devices. That's why we will attempt to produce polymer materials for our 3D printer, synthesizing multiple chemicals and extracting metals from local resources, relevant for future colonization. Speaking of colonization, we will study the influence of the radiation on human body, as well as the implication of living in dusty environment with reduced gravity. That's why we need devices monitoring health conditions, such as thermometers, pulse oximetry, ECG, magnetic resonance imaging, ultrasound, X-ray techniques, as well as positron emission tomography. Moreover, scientists will conduct experiments with hydroponic and aeroponic in our greenhouses. They will even have fishes and study how they function in unusual conditions. The greenhouse will host our crops growing in the soil made of enriched Martian regolith. The fertilizer will be made from locally extracted materials, like sulfates. Success in our scientific endeavors is guaranteed by a well-equipped laboratory. It must include general instruments from geology, biology, and chemistry labs. Moreover, we need special devices, like X-ray diffraction for chemical analysis. To analyze samples, we will also need microscopes, spectrometers, for example, UV-Zyre, and vibrational spectroscopy instruments. Moreover, we must have devices measuring material properties. What's more, our laboratory requires a contained workstation while working with dangerous and contamination-sensitive samples. We'll also need chemical fixation to store our samples for a long time. To conduct experiments with plants, We need environmentally controlled chambers. As you can see, our base camp is just a simple flattened hemisphere. It is fully inflatable, meaning we can fold it and obtain an excellent inflated fact ratio. Base is composed of different layers made from Nextel Kevlar fabric. Except aerogel, all other layer filling will be made in situ, so that means we don't need to bring any additional filling with us. Interior of the base contains living space, lab, and storage space. An inner shield will be filled with water, which is our radiation shield, 30 centimeters thick at the bottom and gradually increasing up to 1 meter at the very top of the dome. To be able to produce energy before the astronauts arrive, we rely on solar panels in the form of flexible, easy-to-unroll parts. It is worth pointing out that such panels are not as efficient as their rigid counterparts. However, for the base area is not a concern, so panels are optimized for power-to-weight ratio. At the time of making this presentation, the best panels can achieve a power-to-weight ratio of 4.3 kilowatts per kilogram. By 2030, this number should reach 5 kilowatts per kilogram, and the durability should be improved. The lightweight of the solar panels was the reason why we chose them as a power source. Another benefit of this is that we can take a large number of panels as a spares without significantly affecting the mass of the overall mission. The situation is different with solar panels for rovers. The solar cells are optimized for efficiency, as the main limiting factor for vehicles is the surface area rather than mass.
Solid oxide fuel cells are the workhorse for our mission's energy production. Not only can we generate electric power from methane with an excellent efficiency, latest technological developments give us reasons to assume that the same machines can be also used for production of chemicals we need on Mars. This enables us to reduce mission weight considerably, besides providing us to produce large quantities of fuel we need for our EVAs. As we use the same fuel cells for energy generation at the base and in the vehicles, we have great redundancy.
Methane and oxygen will be stored in spherical inflatable tanks with a diameter of 25 meters anchored to the ground, capable of holding around 8,000 cubic meters of gas at 1.4 bar of pressure. The tanks are made out of Kevlar fabric with a polymer layer on the inside to ensure hermeticity. The goal of any production on Mars is to use as many resources as possible that can be found in situ. Oxygen for crew can be easily obtained from solid oxide fuel cells. Explosive production starts after astronauts' arrival, since hydrogen peroxide can be stored for a long time. When the ingredients are not mixed together, they are relatively safe for handling by humans. However, it may be desirable to use the self-propelled exoskeletons for handling. Plastic production allows us to produce filament for small 3D printers. Printing will be focused on small scale, for example, for spare parts, rather than printing a whole new base. A completely different challenge is communication with Earth. The delay caused by the distance between Mars and Earth, and because of its finite speed of light, is impossible to work around. What can be done, though, is to ensure the continuity and strength of the signal. We will use a small satellite, probably with laser beam, and antenna placed on the geostationary orbit above our mission area. This would serve as the amplifying midpoint between the main base and the Earth. A radidimensional satellite communication system would require at least 3 satellites covering all Martian longitudes. That would allow us to maintain not only a contact between the main base and the camps, but also would serve as an extra redundant system for communication.
Our EDA suit maximizes mobility and reduce dust exposure to a minimum. The suits will use technologies from MIT's BioSuit, such as chip memory alloy coils, which is expected to be ready in the near future. When entering the suit, it feels loosely, but later it contracts and fits to the body. This allows for the suits to be interchangeable between astronauts. As for the use of multifunctional equipment in our mission, exoskeletons can be used in several different ways. Firstly, they could be worn by astronauts to increase his strength, enabling them to lift 250 kilograms. Secondly, an exoskeleton could be remotely operated by an astronaut wearing a VR headset. Thirdly, the exoskeletons could operate semi-autonomously, guided by advanced AI system partly supervised from Earth. All exoskeletons will have a rescue mode, in which when they detect that the astronaut inside them is unconscious, they will alert the rest of the crew and return to the base autonomously. Rovers have the shape of a cylinder, 3 meters high, 5 meters wide, and 10 meters long. Interior is insulated with aerogel. Forward dome will be made out of strong, transparent, scratch-resistant reinforced acrylic, allowing astronauts to admire the views. Our crew will have two types of rovers, cargo and passenger. Vehicles will have inflatable Kevlar tires 3 meters in diameter. With 3 of them per side, this configuration allows the vehicle to drive over 1 meter high rocks and provides good traction for climbing over large obstacles. The chassis is a lightweight rigid structure located under the outermost parts of the cabin. It is made up of methane and oxygen fuel tanks, fuel cells, and a compressor for pressurizing the wheels with CO2. Our aircraft, after several modifications, won't be only as a means of transportation, but also as a vehicle for emergency situations. Thanks to the high speed it can achieve, it will be able to quickly arrive at an emergency spot, and thanks to the use of autopilot, it will be able to do so without having to engage another astronaut. By making minor changes, we'll be able to reduce weight and increase range. Water extraction is based on a small autonomous devices equipped with magnetrons, microwave generators. Using microwaves, we can boil water from soil directly without unnecessary regular heating. Rover is similar to a vacuum cleaner. It is equipped with a funnel for collecting evaporated water. Next, vapor goes through the pump where pressure is increasing. Thereby, we receive liquid water in pipes. Devices are permanently connected to the base. They don't have batteries or water tanks. Wires and pipes are rolled up in the base and work similar to cable and vacuum cleaner. They are also modular. This allows us to easily increase rover range or change damaged parts. Basic range is 30 meters radius. Sample gathering helicopter is light and compact device representing the next Mars helicopters generation. Basic idea was to help astronauts to collect samples from hard-to-reach places. Helicopters are made up with parts that you can see on presentation. As the only device, they don't have a standard battery pack. Helicopters aren't a critical part of our mission, so they can have different non-exchangeable power source. We decided to use lighter lithium-sulfur batteries. Second power source is solar panels. Helicopters have movable arm under the device. This arm contains anchoring and drilling system. The arm extends, anchored to the ground, and remains rigid, so the drone can turn off its motors and recharge via solar panels, and use this time to collecting samples.
All specialist astronauts must have secondary and backup functions to have all the important abilities for the survival of the team at least doubled. All astronauts have either technical or medical knowledge for emergencies. Engineers specialize in base and vehicle maintenance. The scientific coordinator is a primary geologist and backup biologist, giving him expertise in both fields. Geologists have technical know-how specifically related to their mission to operate drills, explosives, and vehicles. The doctor also does biologic research. The biologist is a replacement of the doctor. Doctor and biologist can both fly the rescue craft. For example, the second geologist in the team has a second specialization for vehicle maintenance, as the geologist will operate far away from the camp with their rovers. As he possesses engineering know-how, he is predestined to be backup of the engineers for life support maintenance at the base camp. In emergencies, the command structure must be clear to assign all team members with the right task to save the mission. Engineers take the lead as they are most qualified to keep the team alive in emergencies. The ground control can only give strong recommendations, as only the astronauts can decide if actions are worth the risk of their own lives. Ground control should take over standard tasks to save time for the astronauts. The scientific coordinator is a primary geologist, as this is the emphasis of the mission, but also has expert knowledge in biology. The doctor has the last say regarding health issues and EVA planning to avoid radiation overexposure.
Our mission is divided into 8 phases. Phase 1 and 2 cover all period before astronauts' arrival. In Phase 1, which starts in 7th month after launch, our supplies land on the planet's surface. A well-thought arrangement of payload allows most of the significant equipment to be automatically unpacked. The base will inflate itself. Phase 2 includes automatic production of water, fuel, oxygen, and food. Taking advantage of the time on the Mars surface, we accumulate supplies and refill tanks. This extra time also allows us to check production and be sure everything works well. In Phase 3, astronauts will organize remaining equipment and will check one more time functioning of all systems. Production of explosives begins. Presence of people on the spot allows to start aquaponics and lab arrangements, since these activities require high precision. Next, in Phase 4, the crew performs some scout missions. Despite the fact that almost all activities will be planned in advance and astronauts will have data about the planet's surface, it will be a great opportunity to compare it to what they will find in situ. Phase 5 and 6 is pure science research. In that time, astronauts will visit as many scientifically interesting places as they can and will collect data about Mars climate, geology, and many more. Crew will be divided into 2 groups. One will stay in base camp, when the second one will be part of rover missions. This allows us to work simultaneously and effectively. Scientific research includes drilling and seismic experiments. Phase 7 includes time directly before astronauts leave. This period will be intended for securing samples and data collected during rover missions and lab experiments. Crew will be prepared the base, vehicles, and all equipment for surviving without them. Also in that phase, astronauts will prepare a movable radio telescope from one of the rovers and aircraft. This idea allows us to reuse some equipment and gain extra scientific data after the end of the mission. Also, that kind of telescope can be used as a giant interferometer combined with Earth telescopes. Phase 8, last but not least. Our equipment can last much longer than 1.5 years of manned mission. Therefore, after astronauts leave, all base camp will stay in standby mode. Devices still will be producing all resources and filling tanks. Automated base camp will provide food, water, fuel, and other stuff for possible next missions. Power production continues as long as solar panels are not degraded by radioactivity, as they are regularly dedusted by the exoskeletons.
We understand that our mission will not receive unlimited funding. Therefore, we plan to explore additional income streams. We want to generate income from IP rights for dual-use technologies. For example, flexible and lightweight PV with automated cleaning can be used in Earth deserts. Lightweight fuel cells can be used for aviation on Earth. Power-to-fuel and power-to-chemical technologies are essential to fight climate change. Exoskeletons for workers and handicapped could serve millions of humans. We can also fund space mining corporations to raise upfront capital. Nonetheless, we are in a position to provide services for future mission on Mars. We can sell methane, plastics, oxygen, water, and algae from unmanned production long after the mission period. If marketed well, these activities could generate a large part of the funding for the mission and eventually generate a profit. Reduction of cost is another possibility. We assume many technologies require to be off the shelf by the 2030s. Of course, a reduction of mission weight could provide immediate cost reductions. We follow two principles to reduce our mission weight below 30 tons. First, we utilize resources we can find on Mars. We use Mars water as construction material for radiation shielding to build up the base Hab. From solar energy, together with Mars water and atmosphere, we produce methane as well as syngas for multiple chemicals, explosives, and plastics. Using synthetic plastic for printing consumables like containers, drilling equipment, and spare parts frees us from bringing these items entirely. Second, we use the same devices and systems for many different purposes. For example, exoskeletons as autonomous robots, as power multipliers for astronauts on EVA, or for being distance controlled. Many devices are interchangeable. That also serves higher redundancy. Solid oxide fuel cells can be used for backup power generation and the same machine for fuel production in reverse mode. Finally, we can reutilize system components for different usage required according to the mission phase. For example, we can transform a rover and a plane into a radio telescope at the end of the mission for unmanned usage. And another example for a final usage would be to have edible furniture as emergency rations. As you see, we try not to cheat on the weights. Please see that we avoid double counting and did not overlook important and heavy parts of the equipment. However, we included the technical progress within the next 10 years that will make many technologies lighter, compacter, and tougher.
All right, thank you very much. That was our presentation.
Okay, we have about 3 minutes remaining for any questions that judges have.
All right. I just saw some other team members in our participation group, and if they want to answer some of the questions, that's totally fine.
Okay, great.
I have a question. Hello, everyone.
Nicole, then Robert.
Okay. On the mission planning slide on your presentation, which was very nice, is that slide a slide your team made?
Yes, that was a slide that we made.
Okay, thank you very much. And on the space mining, are you referring to mining on Mars or on asteroids?
So I think our idea was to start cooperations and already get money upfront for the ideas of mining on asteroids.
Asteroids.
Asteroids, sorry.
Thank you. Thank you very much. Wonderful presentation.
Thank you for the question.
Robert, do you have a question? You're on mute right now. It's the Zoom mute. Try to help you out here.
There we go.
Yeah, go ahead.
Just to be clear, is the only food you have the algae, or are there other foods that you're bringing?
Well, most of our food diet is from the algae, but we assume that the algae is gene manipulated to have more nutrients and other kind of nutrients that aren't there to this day. But we also bring supplement pills, and we also feed different kind of animals like fish some insects to provide more diversity in our diet.
Okay, so you also have fish to eat.
Well, it's kind of an experiment, but on some days, I'm sure there will be a few fish.
Okay.
Thank you.
Any other questions?
May I ask a question?
Yes, go ahead.
How do you plan to work with menu fatigue? Like you expect the astronauts to eat more or less the same thing for 1.5 years. So how do you plan to cope with menu fatigue or something like that?
Well, that is a good question, but I think that wasn't my role in the role. So we wrote a scientific paper, and we can share that later this day, where we describe everything in much greater detail, and that makes things way more clear too.
Yeah, we'll be sending around everyone's reports to the other teams right after this call, so they have a chance to review them before tomorrow.
Okay, thank you.
Okay, thank you so much, Team 1. Great presentation. Our next team is Team 3. That's our America's West Coast team, I believe. Okay, go ahead, you have 30 minutes.
Hello, everyone. Team North America West presents Polemos 1, a mission to Mars focused on creating a foundation for similar missions and the technology that drives them. Set in Milankovitch crater, a location rich with water ice and unique terrain, the 550-day, 28.5-ton mission will reap new information on Martian surface geology and biology. Along with a massive suite of scientific instruments for the Hab, our crew of 4 astronauts will bring along a pressurized rover, redwater ice drill, and spider-like robot Alala to gain knowledge not only on the more scientific aspects of Martian life and living, but the engineering and AI sides of it as well. Polemos 1, with its myriad of technologies tried and tested at home on Earth, sits at the bleeding edge in food production, power generation, in situ resource utilization, and AI decision-making. By the time the mission's 2 possible launch windows open in 2031 and 2033, this equipment will have matured and solidified into a support structure and jumping off point for not only our pioneering first 4, but for exploration of Mars as a whole.
All right. As Peyton touched on, Polemos 1 will land in Milankovitch, a crater 118 kilometers in diameter located in Arcadia, Planitia. This location was chosen because it is one of 8 sites in the Martian mid-latitudes where ice has been found particularly close to the surface in scarps located at 54.3 degrees north latitude and 148 degrees west longitude. Milankovitch also has other geological features of interest, including lava flows, aeolian deposits, and a central peak. Landing there is also a good choice for practical reasons, since the crater floor is mostly flat plains. That means astronauts and rovers should be able to traverse it easily, even at high speeds. The relatively level floor should also make line-of-sight communication between the different elements of Polemos 1 easier. Confirming the presence of large amounts of subsurface ice in Milankovitch is very scientifically important, since if microbial life still exists on Mars, it's most likely to be found in water or ice deposits and briny deposits. However, finding and collecting ice is valuable in other ways for future human missions, since they're likely to need to produce fuel for their return from resources found on the surface. Polemos 1 will help enable that by taking high-resolution images of the area around the landing site during entry, descent, and landing, which future missions can use to navigate to make their search for fuel easier. Now, the image on the left is, thanks for going back, is an infrared image of the entire crater, and the one on the right is a zoomed in section from the southwest rim with our precise landing site outlined with a red X.
The ideal Mars habitat must protect the health and safety of the crew while sustaining productivity. Factors of a Mars habitat include life support systems, radiation protection, ease of both inter-vehicle activity and extra-vehicle activity, habitat space, cost, and more. A first-stage habitat is a temporary habitat, mainly a place to stay during the construction of the more permanent second-stage habitat. TransHab was a NASA inflatable habitat concept developed in the 1990s, with the rights to this concept now owned by Bigelow Aerospace. TransHab has 4 levels featuring an airlock, exercise area, first aid station, personal hygiene area, crew quarters, mechanical room, and kitchen. TransHab is not specifically designed for the surface of Mars, but the design could be and has been repurposed to allow for this. TransHab may not be viable for a mission launching in the early 2030s, and NASA is no longer developing the concept, as Bigelow Aerospace is unlikely to finish TransHab by the 2030s. Additionally, TransHab does not provide any substantial benefits over using a lander as a temporary habitat. In the case of Polaris 1, we're going to be using a lander as a temporary habitat, as it's the approach many companies are taking, and it's very simple, efficient, and most cost-effective. The lander would be used as a habitat for a short time, while the main habitat would be set up. The second stage habitat is a more permanent habitat meant for longer-term stays. Domes are a staple of Mars imagery, but are impractical. They are difficult to build, are not space efficient, nor do they offer any radiation protection. Underground habitats were proposed by engineers in the 1990s, but they were found to be impractical. Building an underground habitat would require more equipment and time than any other proposed habitat design. One advantage that underground habitat does have is virtually unlimited amount of room and excellent protection from radiation. For Polaris 1, our team proposes a custom habitat design to fit the criteria of the mission. Taking design cues from the NASA Habitat Demonstration Unit and other Mars habitat designs to keep costs low, our team proposes a custom habitat design which features a water tank at the top of the head to protect against radiation. In addition, the habitat would be connected to a greenhouse through a pressurized tunnel for ease of access. Amenities include a hygiene module, a geolab, a medical station, a maintenance workstation, a robotic workstation, an airlock, and a separate inflatable crew area. The habitat will come pre-assembled with little setup required. The habitat will weigh approximately 16 tons, and NASA has not provided an estimated cost of the habitat, but it should be low since similar designs have already been researched and created. And here you can see a bit of an illustration of the habitat showing the water tank to protect against radiation.
All right, for spacesuits, astronauts on the Polaris 1 mission will use a modified version of the Z-series spacesuit, which was developed by NASA. The suit's components are meant to work with the systems in both the habitat and the pressurized rover, which will allow the crew to explore larger areas of the Martian surface more easily. The suit helmets will be catered to the pressurized rover, as there will be an airlock on the helmet, allowing whoever is inside the rover to take their helmet off and breathe the oxygen coming from the rover. In addition, the helmets will have a thin sheet of gold on them, which gives protection from ultraviolet radiation from the sun when the astronauts are outside of the Hab or rover and are exploring the surface. The suit will be made out of a nylon tricot base, Kevlar, and a Nomex blend, with the gloves using spandex for extra flexibility. The Kevlar and Nomex will keep the suits very durable and sustainable for the Mars mission, and the spandex on the glove portion of the suit will be needed for flexibility when setting up the Hab, collecting Mars samples, and driving the pressurized rover. The calculated weight of the spacesuit design will be approximately 13.5 kilograms or 30 pounds, and in addition, the life support system and oxygen needed for an EVA weighs 22.5 kilograms or 50 pounds. This comes to a total weight of around 36 kilograms or 80 pounds, making maneuvering pretty easy for the surface. The suits will have an integrated hatch, or aka a suit port, on their backpacks, allowing astronauts to seal their suits to a docking port and enter the habitat and the pressurized rover. This system prevents outside contamination and minimizes the amount of Martian dust crew members are exposed to, since the exterior of the suit never enters a pressurized area.
For the life support system, the crew habitat will be pressurized to 101.3 kilopascals, that's 14.69 psi. The habitat atmosphere will be 80% nitrogen and 20% oxygen. Nitrogen can be extracted from the Martian atmosphere through a condensation process.
So the EVA suits you heard about a little while ago will be excellent for exploring the area near the landing site and the habitat. But during their stay on the surface, the astronauts will definitely need to explore other areas of the crater, which could be more than 100 kilometers away. So to do so, they will need a pressurized rover like the one on screen, which is an artist's concept of the rovers for NASA's austere missions to Mars plan. The rover for Polemos 1 will be similar in both shape and size, even though the rest of our mission is very different. So, first of all, 2 astronauts will be able to attach their suit ports to hatches on the rear of the vehicle to enter the pressurized cabin, which will be able to house them for up to 2 weeks, plus a safety margin, just in case. That leaves them with more than enough time to travel to the other edge of the crater and back, since the rover has a top speed of 20 kilometers per hour. The range of the rover is really only limited by the endurance of the life support system, since the rover's power source will be a scaled-up version of the advanced Stirling radioisotope generator, producing 5 kilowatts of electricity. Since the RTG in question produces power all the time, the rover will never need to stop to recharge or to be refueled. And unlike solar panels, it will still work during a dust storm. Additionally, the heat produced by the decaying plutonium will only diminish by 0.787% every year, so the pressurized rover could probably be reused by a future mission to Milankovitch if the rest of the vehicle was still working. But speaking of the rest of the vehicle, it's worth noting that the consumables for the life support system of the rover will weigh 819 kilograms for every 2-week trip. However, since all of them can be produced at the Hab, the rover will only need to return to refill the oxygen tanks and stock up on food and other consumables. That's outlined in our paper. The rover's scientific capabilities will be limited to weather sensors, visible light and infrared cameras, and ground-penetrating radar to map surface features, including, subsurface features, including ice deposits. Most of the data gathered during the rover expedition will be collected by astronauts in EVA suits using cameras, shovels, and core sampling drills to collect data and specimens for analysis at the Hab. The samples will be stored in containers on the outside of the rover, so the astronauts won't accidentally contaminate them on their 2-week expedition. So to fit all of these features, the rover will be 8 meters long and 6 to 7 meters wide and will weigh 5 tons. Since the rover won't be able to fit on the same descent stage as the habitat, it will be landed separately beforehand so the crew can confirm that it touched down safely before landing themselves.
While massive water mining and fuel production plants like Int'l, which I'll touch on later, have been discussed, operations like that are currently too far off and will probably require an entire mission's time to set up. For Polemos 1, we will use Redwater, a system with scale models already tried and true in thermal vacuum chambers set in a Mars-like environment. The drill used is a combination of traditional drilling with an auger and a special strategy called the Rodriguez well for melting ice and cycling it through a heat source. This creates an efficient positive feedback loop, that uses minimal energy to collect from a well of ever-growing subsurface ice. It requires no special source of electricity and doesn't even need a heater for the water, since that can be run through a nearby kilopower reactor. The two diagrams here show the steps of well formation and water extraction, as well as the internal components of the drill. This should only weigh a few tons, probably around 3.
For the life support system will convert 1 ton of CO2 per day into oxygen from human respiration, which is then supplied back to the crew. The air recycler system must remove the CO2 and supply 1,700 pounds of new oxygen per day, or a total of 617.3 tons of oxygen per year. The humidity will be kept between 20 to 40%, and the temperature kept about 21 degrees Celsius. Daily, humans will use 100 watts of power, so the life support system of settlement, which includes food production, require approximately 100 watts to, or 1%, which is 10,000 watts to 20,000 watts of average power per inhabitant. One person will take 0.8 kg of oxygen, 1.8 kilograms of food, 2.5 kilograms of water, and will give out 1.14 kilogram of CO2, 0.96 kilogram of H2O gas, 1 kilogram of waste, and 2 kilogram of H2O liquid. The CO2 treatment will give out oxygen and methane, which we can reuse the oxygen. The waste treatment will separate solid waste and liquid waste.
How are we going to make an extraterrestrial habitat and make fuel for the trip home? The main requirements of a power source on Mars are weight, cost, output, and design simplicity. NASA estimates 20 kilowatts an hour of power will be needed to power a base. Solar panel, kilopower reactors, and RTG reactors are all options. Solar panels are seen as a quick and dirty solution, but they have many downfalls. They only produce power during the day. They have a limited amount of power output due to dust storms. The distance of Mars to the sun is great, and dilunar oscillation and solar flux reduces efficiency even further. In total, the efficiency of solar panels will be approximately 20%, a low number that would mean an enormous amount of solar panels would be required in order to power a base on Mars. Kilopower reactors are a type of nuclear reactor created by NASA for use on the Moon and Mars. The kilopower initiative started in 2015, and the kilopower reactors can generate between 1 and 10 kilowatts an hour. NASA estimates that 2 kilopower reactors will be required to power a Martian base, and the only downfall of kilopower reactors is heat dissipation, which can be resolved by adding a large radiator to the top of the reactor. Heat generated from the kilopower reactor will also be used to melt ice, as Peyton mentioned earlier. RTG reactors are a type of nuclear battery used in most unmanned space missions. They aren't viable for use on Mars due to limited power output. Palamas will use 2 kilopower reactors to power the base. Kilopower reactors are small, efficient, and cost-effective. The 2 kilopower reactors weigh a total 6.61 tons.
All right. As you heard in the introduction, Palamas 1 is meant to build a foundation for future missions to Mars by testing new technologies, but it is also meant to study Martian geology, the history of the Martian climate, and the possibility of life on Mars, past and present. Thanks to their advanced equipment and diverse skill set, the crew will be able to study these topics in far more detail and with far more accuracy than a robotic mission ever could. Now, assuming the crew can't use the rover to find their way out of Milankovitch crater, which isn't in the mission plan, but it could happen, they will have roughly 11,000 square kilometers of Martian soil to explore. There's no way they can thoroughly investigate all that land in only a year and a half, so they will instead concentrate their exploration on 6 areas, spending 2 to 3 months looking at each one. So on the upper left, you can see a photo of the crater with arrows and labels identifying the areas I mean. The photo is very high in contrast. I apologize for that. And on the bottom right, you can see a draft schedule we wrote up for the exploration of those areas.
Can I see if I can fix that?
Yeah, I think we have a couple seconds for you to, I don't know, stop sharing and start again if you want.
Is that better?
Oh, that's
Yeah,
much
it's
better.
not as flashed out.
Yeah, sorry, that's HDR. I'm not sure why it does that.
High dynamic range indeed. All right, the astronauts will start by exploring the scarps near the Hab, which, by the way, is marked by that red X on the map, just like it was on the high-rise photo of the landing site earlier on. They will do that using a combination of EVAs and rover trips. The rover's ground-penetrating radar will be heavily used to map the ice inside the scarps. It should be able to detect other subsurface features later on, but it will be most useful for this part of the mission. After ice has been confirmed and the Redwater drilling rig is fully operational, which might take a couple months, the astronauts will explore areas of the crater that are further away from the base. For these trips, the rover will be crewed by 1 astronaut with science training and 1 capable of repairing the rover in an emergency. Since astronauts on EVAs won't be able to carry many tools and the rover lacks the space for all of the equipment necessary to analyze samples, they will instead be brought back to the Hab whenever the rover's life support system needs to be refueled. There, the other 2 astronauts will use spectrometers to study the composition of rock samples and a compact color biofinder and signs of life detector to search them for biosignatures. Additionally, water from samples of the scarps will be filtered through an agnostic life finder to search for molecules similar to DNA, and another ALF will be attached to the Redwater drilling rig to filter the water it collects before it's used. Astronauts will also study the history of the Martian climate by analyzing the trapped gases in cores taken from ice deposits. As you can see in the schedule, the last month of the mission is dedicated to sorting through the samples that the astronauts collected and choosing which ones to take back to Earth. Since we were only told that there would be a Mars ascent vehicle available for our crew, we didn't really know how much space there would be to bring back Mars rocks. But we assumed there would be a small amount of room in the MAV for samples, though, since it would be kind of a waste to go all the way to another planet and not bring back some stuff to study, especially since NASA's working on an unmanned mission to do just that pretty soon. But Polemos 1 is likely to collect far more samples than the MAV can take back, so the astronauts will have to choose only the most interesting rocks and ice cores and leave the rest in containers inside or outside the Hab in case a future mission is sent to collect them.
One of the technologies Polemos 1 will be bringing along to Mars is a spider-like rover named Alala. Weighing half a kilogram, she is a scaled-down version of the athlete system that would be used for Mithril, a concept ice harvesting and in-situ propellant production plant on a much larger scale than the Redwater system the Polemos program will use. Alala's larger siblings, just like her, will use 2 software suites to drive both autonomous and driver-in-the-loop functions. To develop a manual of real-life fixes and possible failure modes, All will be brought along on the pressurized rover while astronauts are on scientific expeditions, and an astronaut will be able to test her maneuverability and decision-making skills. In the top right, JPL Principal Investigator Brian Wilcox stands in front of the existing 1/4 scale athlete model. Wilcox has written a paper on athlete and its systems. Created for the moon, Mithril and Polemos will take it to Mars. In the bottom left is a render by the Mithril team at the University of Illinois, showing a full-scale athlete behind a kilopower reactor and next to 2 propellant storage domes and ice mining drill that it will assemble as part of Mithril's deployment. Mithril is designed to be landed in one go in the late 2030s. They hope to send it on a single Starship or SLS.
The agricultural system we chose for the Polemos 1 mission is hydroponics, as is an efficient and relatively undemanding option for Martian astronauts. The system utilizes water sourced from Martian ice, as well as macronutrients such as nitrogen, phosphorus, and potassium, to create a nutrient solution that produces a wide variety of traditional produce. This allows Martian astronauts to avoid a reliance on soil for the plant's nutrients, which is not the most efficient or beneficial option, as hydroponics produces plants 50% faster and conserves 10 times the amount of water. Due to the hydroponic system being located indoors to protect against radiation, botanical grow lights will be utilized as the plant's energy source. The hydroponic grow lights will produce a magenta light frequency, as it combines the benefits of both red and blue light. Red light has been shown to be beneficial in producing taller and leafier plants, while blue light promotes leaf expansion, sprouting, and root development, which are all important factors in the quality and efficiency of plant growth. An additional benefit of a hydroponic system is that it requires minimal maintenance, especially when compared to other options, such as aeroponics and traditional farming methods. Maintenance includes draining and refilling the hydroponic nutrient solution about twice a month, as well as simple cleaning measures to ensure the system stays in its proper condition. The image depicts an active indoor hydroponic system similar to the one being used for the Polemos 1 mission. I'm not hearing anything.
Yeah, if anyone's speaking, we can't hear you.
In the spirit of international cooperation, the crew of the 4 will be selected from NASA, JXA, ESA, and either CNSA or CARI. Each astronaut will be cross-trained in a variety of subjects. At least 2 people will be trained in every aspect of the mission, and there will be 1 person designated commander. This commander will have the final say on important decisions in order to avoid conflict, and if a verbal or physical conflict does crop up, they are responsible for breaking it up. Since you can just send someone back to Earth, since you can't just send someone back to Earth, confinement to quarters would be the highest possible punishment. Because we don't know exactly who our crew will be and what skills they may already have, we chose to leave ambiguous who exactly would do that. Training would be smoother and less heavy if astronauts settled into their existing specialties and trained outside of those, rather than being shoehorned into a designated position. If the Polemos 1 program were to exist, that decision would have to be made shortly after crew selection.
All right, so thank you for watching our presentation, and I don't know how much time we have left for questions. It looks like the 5-minute warning was given.
Yeah, you have about 3 minutes left for questions. Team 6 is the next team. Sorry, I was wrong in the chat. Go ahead. Any questions from the judges?
Yeah. So you've got a crew of 4. Can you say anything about the skill mix?
Well, we want to have, generally speaking, we want to have 2 engineers and 2 scientists. Obviously, we're going to have extreme cross-training. We'll have 2 specialists that are trained in each subject. So in any given amount of crew, in any given 2-person expedition, there's always going to be at least 1 person who knows pretty much everything about what they're doing. So we'll have 2 for EVA duties, 2 for life support system service, 2 for the main 3 surface studies disciplines, which for us will be geology, microbiology, paleontology, 2 specialists with knowledge of how to fly the MAVER lander in an emergency, and 2 specialists capable of servicing the mission's electrical components. So that's life support, but that's also kind of the nuclear side of RTGs and kilopower. And as we said, we don't know exactly what the astronaut selection pool will come to us with. They might have skills that naturally fill this out. There might be a little bit of training that needs to go on, but that's something that should be solidified either during the crew selection process or afterwards.
Okay. Any other questions from judges? Arya, you have your hand up. Do you have a question?
Yeah. You said that you're gonna build an underground habitat. If I'm not wrong,
We're not building an underground habitat.
Okay. Thank you.
Thank you, though.
You can pull up the picture, the render you made of the habitat.
Yeah, sure. Here,
Just
maybe I can
describe that in a little more detail.
chat.
Yeah.
Let me find it.
We're just about out of time. So we'll be sending out the presentations to everyone, or the reports to everyone. We can also, you guys could also elect to send your PowerPoint slides out to everyone as well. We're going to go ahead and move on now. We're out of time for you guys. Good job. That was a great presentation.
Thank you.
Okay, our next team is Team 6. Team 6 is America Central. Go ahead, you have 30 minutes.
All right. Our expedition is the Niger-Vallis exploration mission, and for the location, we decided, since this is difficult, everything has to be. So we used
Show
the
yourself.
program to NASA with information. Yeah, I don't have a camera.
Oh.
I don't have anything to do that.
If you could speak up a little, though, your sound is really low.
All right. So we used a program to developed by NASA with the information about the planet in different areas, and we decided on a spot 35.49 degrees latitude and 92.34 longitude. The site is along the Niger-Vallis, an area to the east of the Hellas Planatia, and the site was found using NASA's Mars trek, in which we used its tools to find a site with ice, gullies, and potential for microcellular paleontology. And additionally, the flat area surrounding the valley will make for an ideal landing zone. The crew will be allowed 20-kilometer work radius so they can find any needed information within their short stay. Plenty of ice can also be found in the area, so ice coring will be quite efficient, although the area is not very level throughout the whole space. There is enough flat area to land and set up the base. From there, multiple hills are present, but they're small enough that a basic rover can traverse them.
For our crew, we are doing 5 members. We're going to have an engineer who is our captain and will also pilot the ship on the way there. He will be making sure that the technology is in order, and also they can work the drills if needed. The glaciologist is from NSIDC, which is a ice research center in Antarctica, and they know what to look for in the ice and can also man the ice core, the ice core drills if they need to. The biologist is keeping track of the algae that we're bringing and making sure it's doing well, and also is going to attempt to keep the Hab clean. The doctor is going to be tracking the
health, both physical and mental, of the crew and trying to keep them in shape. And will also help the biologist clean the Hab. As a bonus, they can also work with the climatology aspect of our mission. And the geologist will be working with the engineer and the rover to go out for different research means in the field, and we'll also be working with the archaeology a little bit. For our food, we're going to bring MREs, potatoes, and some different multivitamins. Every day, the meal will consist of an MRE, about 5 baked russet potatoes, and some multivitamins for however many they need per day. With about 2,000 calories per day, they will get what they need to survive. And since we're staying for about 6.5 months, we're going to need quite a bit of food. But for a bit of a diverse diet, and also so they don't get too tired of what they're eating, occasionally they can eat algae and seaweed that will be raised in the base. Our total mass for the food is 1.04 tons.
Our scientific objectives for this mission are, we have 5 of them. Number 1 is to do geological surveys to look for evidence of sedimentation. Number 2 is to do archaeological work to find evidence of past life, as this was a place with water. Number 3 is to test the ability to grow algae on Mars, which would provide both a source of oxygen and nutrition. Number 4 would be seismological surveys to detect any underground activity in the region. And finally, we would be able to test the production of water on Mars through distillation, as the area is covered in an icy mantle. For the geology aspect of this, we'll bring along several coring drills, which will be used to extract both rock and ice cores. Using numerous methods, including the potassium argon dating and microscopes, we will be able to find both the composition and the age of these cores, which will allow us to find how the area might have been in the past and how it is now. Additionally, we can find the composition of the rocks, which can also tell us a little bit about what the area used to be like. So, for example, if you find minerals that could only be formed in a water-rich environment, then you would have substantial evidence for the fact that this area used to be an outflow channel. For the next aspect of the mission, which is the algae growth, then we would be able to find not only how the algae grows on Mars, but also what it can be used for. As of now, the things we have set for the algae are to, number 1, provide a source of nutrients for the crew, and number 2, provide a source of oxygen scrubbing. So instead of bringing along an expensive oxygen scrubbing system, this would actually be able to do most of the work. In experiments done by the Russians during their BIOS-3 experiment, they found that for chlorella algae, which is the species we are bringing along, you'll need about 8 meters squared for a single adult human. So you'd be bringing only about 50 for our 5-man crew. Additionally, they are high in many sources of protein, fiber, and micronutrients. The only caveat is that we would need to prepare and eat them correctly, as they do have a very tough cellular casing. Next up after the algae, we have the archaeology aspect. So Niger Vallis used to be an outflow channel from what we believe, and due to this, sedimentation would have built up in the area, providing pretty good conditions for fossilization. Any sort of large fossils probably wouldn't have survived this long, so we will actually be looking for trace fossils. So that will be things. So that'll be things like tracks or indent fossils, which are the impressions an organism leaves behind when it falls to the ground. Finally, we will be doing the seismology, and the seismic activity is going to be a pretty key factor of the mission. So around the area, we're going to have a network of between 5 and 10 small seismographs, and their data will be reviewed daily. So using this, we'll be able to find not only how impacts will be affecting the surface of Mars, but also any sort of internal activity that might be occurring. Additionally, we're going to have some ground penetrating radar set up to find the internal makeup of the Niger Vallis. So we might be able to find any underground areas.
since the entire region is covered in that aforementioned thick icy mantle. And finally, in a sort of combination of the life support and science, we will be able to test how we would produce water on Mars. So our primary method for this is going to be distillation, where we would take the dirt from around the base, which is a combination of a lot of ice combined with the Martian dust. And this would be put through a series of filters and distillers until finally it would go into a water recycler where any perchlorates and remaining chemicals would be removed, where it could then be used for various things around the base, like hygiene, drinking, or for the algae beds. Additionally, we won't have to produce any extra heat for these, as we can just use the heat produced by the kilopower reactor that we have on site for providing power.
All right, the Mars Habitation module, we're gonna make an inflatable structure, which would be deployed right when we land on the Martian surface, and it'll be holding 5 crew members. It will be equipped with lasting over the designated duration of the mission for extra 50 souls in case there's a reason that we'd like to stay a little longer. The dimensions of the Hab would be 8 by 12 meters. With main materials being used would be the Kevlar fibers, which are 1/2 inch thick, which would be connecting to our floor pattern, which are supported by aluminum beams to help support the second floor. Which we'll have with a total space of 226 meters squared. Our radiation shielding will be provided by a combination of water between the layers of our Kevlar fibers, which would be also reinforced by bismuth infused panels behind them. The total weight of the Hab, with it being unfilled, is 3.1 metric tons. And then the upper floor will be consisting of research and computing data, and the lower floor will hold algae tanks, which will feed oxygen into supplies where it can be sent out throughout the base. We also designed a rover to bring along, and it will be for human operational use. It will also be unpressurized. Its main use is going to be to carry cargo, supplies, experiments, samples, and more. This will be used for example, like going out further away from the habitat to maybe set up little sites for certain places of interest like experiments. It'll be powered by an electric motor with 2 solar panels on the top part of the rover, with additional capability of being recharged at the base. The rover will also have a detachable trailer in need of hauling larger equipment for say, maybe even extra crewmates if we need it, because currently the core rover would sit 2 people, but you could hold, I guess, if you wanted the entire crew with you at once, but mainly the trailer would be to carry around maybe specific scientific instruments like geology equipment and seismology equipment that you want to measure a particular area. And the trailer can be very important for these things. And the core rover sits 2 people. And the total weight of the rover is about 4 tons with the trailer included.
Okay, so the suits that we'd be wearing during the mission are quite similar to the Dava Newman's biosuit that's made out of shape memory alloy, or SMA, which can be returned to its original position after being changed. Designs on the suit are made to apply mechanical counterpressure, resulting in the gas pressure being avoided almost entirely, since human conditions can be seriously affected by radiation. This design will be a huge help for our crew. And for our energy production in the NEM mission, we will be using on-site power, which is going to be a miniature nuclear reactor being developed by NASA called Kilopower. While current designs can only produce up to 1 kilowatt, future designs are expected to provide 50 kilowatts of power, which will be sufficient to power the base and everything within the base. Thank you guys for listening. Do you guys have any questions?
Okay, we got about 15 minutes or so for questions. Any questions from the judges?
What is the temperature of your location? Highest temperature and lowest temperature and average temperature, if you have that information.
I'm not 100% sure if we have that information. I'll consult with my team.
Thank you. I'd love to have that by tomorrow if you can get it.
Okay. Question.
Go ahead, Robert.
What is the design of your Hab? I may have missed it.
The Hab design is going to be an inflatable Hab that, once inflated, would be supported by an aluminum structure inside that would provide enough support so that it can be inflated, but not enough support to keep the entire base together. Plus, the aluminum structure would also support a secondary floor to our base.
How big is it?
If I go back to the slide with the habitation module, the dimensions would be 8 by 12 meters.
This would be in a cylinder. So since this is a 2-floor layout, this would be about 226 square meters of space.
Okay, thank you.
Any other questions?
Yeah, I have a question. First of all, very good presentation. It's great to see you all coming together. My question had to do with astrobiology. I noticed that you said something about sedimentation as far as like past life. Is there any interest or any way that any ideas that you have on how you would be looking at astrobiology? You know, would you want your biologist to be skilled in that area? If you did want to explore that, you know, how would you go about doing it?
As I said before, we're not really looking for current life, as the consensus right now is that Mars can't support life. We'd be looking for signs of past life, so things like trace fossils or I believe they're called impression fossils.
Okay, thank you.
Any judges, any other questions? Okay,
Wait, just to review, okay, your crew is 5, and how long are they going to stay on Mars?
I believe that we were saying for 6 months, but we have the capacity to stay for, I'm pretty sure my team member had said 7 months. Is that what was discussed, team members?
In an emergency, you could stay for up to 8 months in the Hab.
Okay, we could stay up to 8 months. The mission plan is to only stay for 6 months. The goal is to just extract as much scientific data as we can and then leave and analyze it on the way home.
Okay. Robert, any other questions?
No other questions for me.
Okay. So we'll do students now. I just want to remind the students, this is not the criticism round, that's tomorrow. So please stick to just questions, like informational questions. Go ahead, Peyton.
For the radiation shielding, I heard you say you were using bismuth. Is it pure bismuth or is it a bismuth polymer?
It would be bismuth infused panels, as this document shows. I was not part of the group who did this, so if any team members who were participating in this would please speak up.
I will speak up on that. The Hab would not only be covered, the sort of interior portion of the Hab, the wall would be covered by the water shielding, and the entire surface of the Hab is covered by bismuth infused acrylic panels. So these panels are similar to what's used in military testing along with hospitals. So they will be more than accurate protection.
Thank you.
Yeah, I have one question.
Go ahead, Gary.
Okay, thank you. I have one more question concerning the rover. You spoke about the rover. Can you tell me a little bit more about this? Is this something that you intend to design? Do you have any sketches? Could you just tell me a little bit more about the rover?
Okay, I'm
Oh, I got
Pretty
it.
sure Nathan has
Yeah.
the answers to these questions.
All right, so the rover, like I said, it's not really that big. It's a pretty small rover, just meant really for hauling things and people around for different sites to set up. I did sort of make a model. I don't have that picture made up because it wasn't really finalized, but it's really just a small rover capable, going over your typical mounds on Mars, can carry, just it's pretty much just to carry things around and take experiments to place.
All right now, thank you.
I have a question.
Go ahead, Arya.
You said that the rover will be unpressurized, especially considering that you are going to be transporting humans as well. Then could you explain why the rover is unpressurized?
We have an unpressurized rover because if I make a blunder, my teammates will jump in and correct me. But from what I understand, it was because we have a smaller operational radius. So the trips are only meant to be 1 day long, and then we go back to the habitation module because we're not planning on any overnight trips. That is what, and we also left it unpressurized for weight savings and for simplicity.
Thank you.
Any other questions?
Nope.
Okay. All right. Well, thank you, Team 6. Thank you for your presentation. Good job. Our last team for today is team number 5. That's our America's East team. Are you guys ready to present?
Yeah, I'm getting my slideshow pulled up.
Okay, you have 30 minutes. Good luck.
Hold on, it's not letting me share. Shreya, could you share this?
Sure.
Can you all see? I'll put it in percent. There we
Yes,
go.
we can see it. Yep. It's in the presentation bar now. Yes.
Okay, so we are team 5. Our team is Shreya Sawant, me, Kia McNish, Omari Hudson, and Uzair Muhammad.
And Brian Barlow.
Oh, and Brian, yeah.
Next slide.
Yeah. Okay, so our crew consists of a pilot/botanist, a nuclear engineer who is also a mechanic, an astrobiologist, and an aerospace engineer. And then this is the beginning of my science section. Okay, so for our landing site, we chose Utopia Planitia. And the reasons why we chose this is because it has very large ice deposits. Some estimates say that there's as much ice underneath the surface as there is water in Lake Superior. It has relatively flat terrain, which will allow us to land very easily. Also with mud volcanoes being close by, and it's close to several other smaller points of interest. And so our main objective is to study the effects of Mars on humans. And this is our main objective because this data can't be gathered by rovers or robots. It's something that's completely unique to a human mission to Mars. And this will help us understand how the Martian environment affects humans. And this can also help us know what to do better on future missions to improve our astronauts' health. So our goal is to help our astronauts maintain peak health during their stay on Mars. Okay, so ways to study the effects of Mars on humans. We plan to study the effects of the Martian environment, such as Martian gravity
and the different weather and everything on Mars. We also plan to study the psychological effects of a long-term stay on Mars and how contact with relatively few people might affect their mental state, as well as doing experiments on exercise and neuroelectrical muscle stimulation for preventing muscle atrophy. And there's a couple of others on here. Okay, so we'll also be doing some astrobiology experiments, such as ALF device experiments to test for life in Martian ice, and possibly doing a long-distance EVA mission to study hydrothermal vents. We also plan to study Martian weather, such as dust storms, and we'll be doing Mars environmental dynamics analysis and studying different weather using radio suns, drop suns, and cameras. And a lot of different information can be gathered from Martian rocks, so we plan to do a lot of geology missions as well, such as stratum data collection to study the geological history. We're going to observe glacial patterns, gather information about the Martian climate, and try to figure out its history. We're going to analyze different ice layers in the cryosphere of Mars, as well as observe the mud volcanoes that are in Utopia, and possibly do a long distance EVA to study lava temperature or lava tunnels, and do some internal temperature measurements and seismic activity measurements. We're also planning on growing crops on Mars as one of our main food sources. And so as well, along with our aeroponic greenhouse, we will also be doing experiments in Martian soil to see how the growth compares to our aeroponic greenhouse. And we'll also be trying to figure out what GMOs to use for future missions to increase our harvest, and doing some experiments in Martian sunlight as well. And for planetary studies, we will be mapping the movement of Martian moons and seeing how they affect the planet, as well as investigating methane spikes that appear on Mars.
So, hi, my name is Shreya, and I'm the engineering department. So let's get started. The engineering objectives. Our engineering objectives are to see what technologies used on this mission do not work as expected, succeed, or can be improved on. And everything can be improved on, and in my opinion. And our second goal is to test experimental technologies that can be used or expanded upon in future missions. The habitat is a two-story inflatable structure. The first floor holds the entrance airlock, decontamination chamber, EVA prep room, medical bay, lab, outside material loading dock, water processing unit, and storage space, with the rest of the payload stored in the lander. An attached inflatable greenhouse is where the Marsnauts will grow their crops using aeroponic towers. The lab also serves as the emergency shelter, as is in the center of the Hab and puts the most mass between the crew and the outside world. The second floor is the Marsnauts living space, which holds the cabins, recreational area, gym and laundry, food prep and dining, bathroom, and office and control center. An important goal of our mission is to keep Earth-borne microbes from exiting the Hab and from Martian dust from entering it, to ensure the lowest risk of planetary contamination for Earth and Mars, and to prevent any risks to Marsnauts' health, such as from inhaling this dust. For Earth and contamination of Mars, the LIFE device, laser-induced fluorescence emission, scans and identifies the microbes present on a surface. Anything exiting the Hab is claimed with isopropyl alcohol and hydrogen peroxide until deemed acceptable. For Mars's contamination of the crew, Hab, and potentially Earth comes mainly in the form of dust. Martian regolith is electrostatically charged, what makes it very, very clingy to surfaces. The Apollo astronauts faced a similar problem with charged lunar dust, which irritated the eyes and nasal passages, and astronaut Harrison Schmitt actually had an allergic reaction to lunar dust. But since then, many technologies have been developed to combat this issue. So, the outer layers of the EVA suits use an electrodynamic dust shield made from a network of carbon nanotubes,
When a high voltage charge is applied to this network, an electric field develops and levitates the dust off the suit, which then can be blown away or brushed off. Surfaces are also coated with layers of indium tin oxide, a material that can dissipate buildups of electrical charge, therefore removing the dust. Electrostatic precipitators will be used to filter atmospheric intakes such as CO2 by capturing dust particles as they travel along a gas stream, where two electrodes on either side of the stream remove the charged dust. The four-seater pressurized vehicle. The mission uses two vehicles, a four-seater vehicle and a two-seater buggy. So a four-seater has a max speed of 40 miles per hour, is 23 by 8 by 12 feet tall, has a suspension system, retractable window shutter, and is equipped with Int'l mesh spring tires, which use shape memory to motor on obstacles and has excelled in simulations of Martian terrain. The vehicle has EVA capabilities and has storage space for samples and a tank for transporting water to the Hab, with an outside material loading hatch that directly connects to the Hab's laboratory or its water processing unit. There's also a small cabin with 4 seats and 2 beds, as it's intended that the crew will take turns sleeping, so someone is always alert and awake to monitor their surroundings. The vehicle is equipped with a ground-penetrating water radar and a Mars Environmental Dynamic Analyzer to keep track of the weather. The vehicle is powered by advanced Stirling radioisotope generator and uses a radio wave system to talk to the other vehicle, Hab, and satellites for Earth. The vehicle can sustain a full crew for up to 6 weeks, allowing for long-distance travel. Here's a basic diagram of the 4-seat vehicle. So the 2-seat buggy is modeled after Apollo Lunar Buggy and a Textron Wildcat X. It's an open-roof extreme terrain vehicle meant for short-distance travel, such as for transporting materials to and from the habitat, lander, and Martian ascent vehicle. It has a radar, a suspension system, Int'l tires, and an attachable drill rig. The buggy's maximum speed is 55 miles per hour and is powered by a rechargeable battery. Navigation. To navigate Mars, the crews will use the high-rise camera on the Mars Reconnaissance orbiter to create image maps that mark important locations by taking pictures of the vehicle as it travels along. Precise data will come from the vehicle's inertial measurements, photographs of the landscape, and the dead reckoning method of calculating distance. That was used on 2 rovers, I believe, the Sojourner and another one. Energy source. Nuclear energy is best. Solar power was not chosen for this mission for 3 main reasons. 1, being farther away from the sun, there's a less amount of power, sunlight received on Mars and only during the day. 2, dust can accumulate on solar panels and render them unusable during dust storms. And 3, the amount of panel surface area needed to provide enough energy for the mission would be difficult to maintain and a heavy payload. On the other hand, nuclear offers a compact, lighter, and an uninterruptible source of power. Krusty was chosen for this mission because of this, as a 10-kilowatt reactor will only stand 11 feet tall and weigh 4,400 pounds, and has a very low likelihood of becoming a nuclear hazard. This mission is powered by 2 Krusty 10-kilowatt reactors. The Hab will communicate with Earth with an optical laser system based on the LCRD payload. Past missions have used radio wave communication, which has a very limited data rate. Optics overcome this barrier by having a bandwidth 10 to 100 times stronger, which means you can send more information in a single transmission, while the payload of it also being smaller, lighter, and less power consuming. A map of Mars that would usually take 9 weeks to send can now take roughly 9 days. This allows for the crew to have better coordination with researchers on Earth. So the mission uses 2 drills, the mechanical drill and the hot water drill, which can be attached to a drill rig present on the 2 vehicles. The mechanical drill can reach depths as low as 10 meters deep to collect samples or to reach water deposits. As stated before, our landing location, Utopia Planitia, as detected by Sherrod, possesses large water deposits at least 10 meters underground. To find them, a ground-penetrating water radar based on a Perseverance rover's RIMFAX instrument will be used. After a usable deposit is found and a mechanical drill has cleared a way down to the deposit, the hot water drill is deployed. This drill melts the deposit's ice to create a cavity of water. A rod well is then installed on the deposit. A pump is submerged into the cavity of melted ice and cycles heated water to prevent refreezing and to melt more ice in the deposit. The water is pumped up to the surface to either be reheated or transferred to a water storage tank within the 4-seater vehicle. This water is brought back to the Hab for analysis by the ALF device and for further processing. Martian water has perchlorates, which can be hazardous to humans. but by using a simple catalyst inspired by anaerobic microbes, more than 99.9% of this perchlorate can be removed from water at room temperature and using hydrogen gas. A briny water electrolyzer will be used to separate water into hydrogen and oxygen. When operated in a simulated Martian environment and with the same input power, the electrolyzer made more than 25 times the amount of oxygen that was produced by the Moxley experiment. To recreate an Earth-like breeding mixture in the Hab, imported tanks of nitrogen will also periodically release gas into the Hab, and trace gases from human metabolism are collected using activated charcoal filters. Additional water is made with the Sebastian process, which takes hydrogen and CO2 to produce water and methane. The hydrogen needed for the reaction is produced by the electrolyzer, and the CO2 is sourced from the exhalations of the crew and possibly atmospheric intakes. Methane is a rocket fuel that future missions can use for a return trip to Earth. Methane is more stable and can be stored at more practical temperatures than liquid hydrogen. As methane is also denser than liquid hydrogen and requires less insulation, storage tanks can be made smaller and therefore cheaper. Passive radiation shielding. So there are two main types of radiation that Marsonauts will face. Galactic cosmic rays are high energy particles speeding around space that constantly bombard Earth and Mars. Solar proton events are when particles near the sun are launched out to space during a solar flare. These events are short-term, but will expose a crew to elevated amounts of radiation. Marsonauts will usually receive a warning from Earth about SPEs beforehand, in which then activities inside the habitat are temporarily canceled. If the crew is too far from the Hab, such as on a long-distance journey in the four-seater vehicle, they'll don their EVA suits and take cover in the storage compartment, which they will be shielded by the water tank, food, supplies, and samples. Hydrogenous materials are the best protectors against radiation. Heavy elements like lead produce more secondary radiation, which is the result of the previous absorption of radiation in that matter than lighter elements. And this secondary radiation is just as dangerous as primary radiation. So some passive radiation shielding materials used are HDPE, a cheap but effective blocker radiation, Kevlar, although more expensive, is just as effective as polyethylene and is a highly durable material that protects from wear and tear, and 20% hydrogen-loaded boron nitride nanotubes woven into fabric, which surpasses polyethylene's ability to block radiation and has excellent mechanical and thermal properties, possessing a higher elastic modulus, melting point, and thermal conductivity than the commonly used alloy aluminum 2195. A potential material that I looked into for shielding is lithium hydride. Also, although able to widely outperform HDPE, it was not chosen for this mission because of its powdery texture, hazard to human health, and high reactivity to water and oxygen. So if anything happens, then this is material that you not want in contact with your life support systems. Spacesuit. The Marsonauts have two suits. The IVA suit is an adjustable mechanical counterpressure suit, while the EVA is partially a gas pressure suit that protects from extreme temperature, environmental conditions, and radiation, and provides life support. Two technologies from the NASA Hot in Mars project used in our suit are the Collins Aerospace ITIS and the Intention Astronaut Smart Glove. The ITIS is an AR display on the visor which shows Marsonauts' vitals, EVA elapsed time, maps, notes, task checklists, and other stats, which allow the Marsonauts to be more independent on their EVAs. The Intention Smart Glove uses gesture technology to control robots instead of using a handheld controller. A drone can be controlled using the Smart Glove or from the vehicles in a Hab. This drone can aid in monitoring EVAs, providing video for Mars, and conduct research with a small drill for collecting samples at unreachable locations. 3D printing can officially create needed parts from scratch. The Marsonauts computer network will include a database of programs instructing a 3D printer how to create certain parts, and a CAD software will allow the Marsonauts to design their own parts as well. So to collect more information about the atmosphere, the Marsonauts will periodically release controlled solar Montgolfier balloons equipped with radiosondes, cameras, and dropsondes, as mentioned in the science section. Radiosondes will measure the atmospheric variables, while the camera will help with obstacle avoidance and provide visual data. The balloon will attempt to deploy the dropsondes, which are dispensable devices used to study storms on Earth over Martian dust storms to study this phenomenon better. An engineering demo done in this mission is testing a localized magnetic field produced by a superconductor. Superconductors produce stronger magnetic fields than conventional materials, while also being lighter. Some high-temperature superconductors can operate in similar ranges to Mars's temperatures. eliminating the need to import cooling agents for the superconductor to work. To determine the efficiency of the generated field, Mars also measure a radiation dose inside the field and compare that to current surface radiation levels and to passive shielding. Thank you. And I'll now pass this presentation on to life support and human factors.
I can't start a screen share while you're sharing.
Okay, let me see if I can.
I can stop your sharing if you need me to.
Wait, found it. Okay, thank you.
So, hello everyone. I am Brian Bartello, and today I'm going to present the life support and human factors. Can everyone see this all right? All right, amazing. Oh wait, that's the end. Wait, what? Okay. This is a topographical map of Mars, which is important to determine where we want to construct a settlement. So we have some mountains up here on the left. We have a lot of lowlands. The blue is lowland, which is good because you're closer to the core, which could help with scientific experiments. And as you mentioned, some of our crew roles, we have a nuclear engineer and mechanic, a scientist, an aerospace engineer, and a pilot/botanist. And all of our crew will be trained in first aid, and will have an ability to communicate with family and friends on Earth and have distractions like movies or games to stay mentally healthy as well as physically healthy. So we're going to start with talking about the sustenance for these astronauts. We're going to look at food, water, and air. So our guiding principle is that since we're doing this in about 2030s, we're gonna take innovations that are maybe experimental and master them, and they'll be a little more ubiquitous in 10 years. So we're going to carry 2,000 pounds of food for the 4 crew members. We're going to carry our seeds to Mars to plant them in regolith in the aeroponic greenhouse. This is good for not only science, but we're also going to be able to grow out food for the astronauts as a side bonus. And we're going to be 3D printing food, and we're going to have water purification and a recycling system, so that way we don't have to bring as much water and weight. We'll carry 350 gallons of potable water for the crew. Wait. 30, I think it's 3,500. Sorry, I'm missing a zero. Anyways, we'll carry 3,500 gallons of potable water for the crew. And the water recovery system is about 96% effective. And the ECLSS is the ISS system. It recovers water from urine and will help keep the cabin humidity condensate from the crew sweat and from the air revitalization system. And the brine processor will increase water recycling on the ISS and will allow our system to work more efficiently so we can bring less water. And we'll have some radiation protection medicine. This is important because we don't want any of our astronauts getting sick. We also want to have virus screening in a way to isolate sick settlers so that viruses don't spread among the humans. And we also don't want that coming back to Earth because that would be even worse. And we also want to have a way to take care of human waste and landfill trash. And then we have a Mars suit, then the Mars suit. And there are a bunch of companies like Planetary Protech, Planetary Protech with Dr. Kuznets, Jean Grace, and Cameron Smith working on this currently. And it was pretty cool to see them in the Humans to Mars Explore Mars conference because they gave a demonstration about their spacesuit. But for our helmet, we're going to have a visor cleaner and a radiation protector. These are important. The visor cleaner so that they can always see and they don't have to take off their helmet in the Martian atmosphere. That wouldn't be very good. Radiation protector, we don't want the astronauts to get too much radiation because Mars is a very thin atmosphere and it doesn't give very good radiation protection. And we should have a smart technology screen and have like a toggle with an AR display or a VR to be used with robots for exploratory missions. For example, if I'm exploring and then I determine I don't think I'm in a safe place, then I could switch to the VR and AR and just look through my robotic rover and see if it's safe.
And then we have the gloves with many special functions, but we're like a button to just basically just call SOS. It's got like communications, and it's got a multi-tool with like maybe a hammer, knife, shovel, storage. And we've got a GPS tracker and locator built in, so that way the astronauts don't get lost in space like Mark Watney. And then we have the suit. This should be light enough so that the humans can still wear it without being too weighed down, and it should be repairable and strong with radiation protection again, so our settlers don't get sick. And our boots should be rugged enough to handle Martian soil, but still not too heavy. Maybe they should be spiked, and they definitely should be repairable. And then with radiation, I'm just going to look over this. So we have a radiation protection system to mitigate the negative impact of radiation on the first settlers that are coming to Mars. Hopefully NASA will challenge researchers to help develop innovative protections to block radiations. And NASA already has some radiation protection materials such as polyethylene. This is nice and cheap because it's commonly found in water bottles, and it's a good candidate to block radiation. We also might end up using boron nitride nanotubes, which are BNNTs, tiny nanotubes made of carbon, boron, nitrogen, and hydrogen. And NASA's been using this system to make yarn, which like special radiation protection yarn, which will provide protection from radiation to the clothing of the astronauts. And then we'll have our habitat. We'll try and make our building materials out of Martian materials, or they should at least include them, which will reduce less mass that we need to bring for expanding the settlements or adding things on Mars.
You've got about 5 minutes left.
Okay. Well, we need weather protection, the ability to create a reliable shelter in order to have a quality of life and explore safely. The shelter should be easily repairable and expandable. It should have an oxygen filter so that's scalable, and it should be modular in case of an oxygen leaks or if there's an emergency, and this segment needs to be secured or detached to help save the rest of the shelter. And tools can be 3D built. Therefore, CAD expertise is at least expected. And then here's just a couple maps, another large topographical map, and another that's all. All right, we just want to say thank you so much. Thank you so much to the Mars Society, and yeah. Thank you for the Mars Society for providing this opportunity, and our mentor, Haritina Magasanu, for advising us, and all the audience here for listening to us. Any questions, anyone?
I have a question. This is Nicole Willett about the water. It was mentioned 2 times, once in human factors, and I just assume for 3D printing, you're going to need some type of water to mix the regolith. Will you be checking for biological hazards in the water before you use that for either 3D printing or human factors?
Yes, our pilot is a biologist, so they will, after we've already landed, they will be in charge of the biology and checking the water to make sure it's safe to drink.
Thank you very much.
Any other questions from judges? Robert, you're on mute.
Okay, 2 questions. How long are you staying on Mars? What, you said 2,000 pounds of food, what food?
So 2,000 pounds of food, really a variety, but we're gonna be 3D printing some. We're gonna make sure we have protein. So we're going to 3D print meat and use cell division on ship. So that way we don't have to bring full-scale animals, which weigh a lot, but we can bring the cells and we can use the cell division to create meat. So you're going to actually culture meat, but you said you're bringing 2,000 pounds of food.
Well, yes,
By 2,000 pounds of food, do you mean 2,000 pounds of apples, pears, carrots, and steaks, or what? What are you
there's
bringing?
various foods for the trip there, and then once they land, once for while they're waiting for the plants to grow. Once the plants have grown to full scale, then the food rate slows. So that's why we calculated 2,000. So that way we and we're also going to dehydrate the food because water weighs a lot, and we have enough water to drink that we've already brought, so we don't need the extra. And what we're going to do is we have enough foods so that we have enough foods that once we land, we can wait until our plants are grown, and then we can start to slow down the rate that we eat the brought food and eat more of the plants.
Okay, thank you.
To answer the first question that you asked, we're staying for roughly 1 year or 355 Martian sols.
Any other questions from judges? Okay, Peyton, you have your hand up. Question?
To what degree will you guys be implementing VR and AR in your suits?
Yes. Do you want to finish your question?
No, it's all right. It's all right.
All right. For AR and VR, for AR is for the Collins Aerospace Informatics Display System. It will provide a projection of any stats or task checklists, like how much time the EVA has happened, how much time in the EVA, or how much oxygen you have left and display inside the visor. And we'll also be using VR to help the Marsnauts feel like they're back on Earth, like part of their recreational activities. They can bring in their headset that can be used to see sights of Earth. So that'll just help them psychologically. And it can also be used to see the footage captured by the weather balloons and the drones.
All right, thank you.
Okay, last question, Arya.
Yes. Could you talk a little bit about the water recovery system? I'm not sure if you elaborated too much on that, but how is the efficiency 96%?
So our water recovery system is based off of the water recovery system on the ISS. And we estimated at around 96% efficient because it not only uses things like urine, but also condensate and some of the air that we exhale and the moisture from that to recycle the water. And so we also assumed that the technology would improve slightly over the next 10 years. So we estimated it at around 96% efficient.
Thank you.
Okay, thank you so much, Team 5. That was great.
Thank you very much.
Good job to everyone today. I think all these presentations were excellent. I think everyone should feel very proud of the job they did today. You all represented yourselves and your teams very well. So congratulations. Robert, do you have any final comments before we end the call?
Once again, I can only reiterate what James said. I think you guys you did a great job on the reports. You did a great job on the presentations. And I want you to know that, by delivering in this way, because ultimately it's, you guys have been delivering. I gave one lecture, a bunch of other people gave a lecture. You're doing all the work here. You may be able to prove the validity of a new way of teaching, which I hope you agree is more interesting than sitting at your desk and just listening to someone lecture at you and then studying for tests, and so that you can help liberate students around the world from boredom that you have had to endure now for 10 or 12 years, or at least liberate them a little bit. So free the students.
Okay, anyway, see you tomorrow.
All right, good morning, everyone. So we're here for round 2 of the competition. These are the critiques of other teams. So the only request I've gotten is for Team 1, Europe, to go a little bit later in the session because a few of them are wrapping up another summer camp they're in. I think we can probably start with the Asia team, Team 2, again today, just because it's so late for them. So Team 2, are you guys ready to start?
Yep, we're good to go. Let me just have our other teammate load up our presentation through screen sharing. We'll just get started.
Okay, I'm starting the timer. You guys have 30 minutes.
Okay.
Can you guys see it?
Yep. Okay. So we're going to start off with the general issues that we found with a lot of the teams first off. So one of the biggest issues that we found between all the teams is radiation. Although the ISS, the astronauts on the ISS are exposed to a lot of radiation every day, the astronauts on Mars without any form of radiation protection would be getting up to 2.5 times higher the radiation that the astronauts on the ISS experience. This leads to about 8 rads of radiation per year. And although this radiation itself year to year isn't going to be too detrimental to the astronauts for like cancer risk and all that, the biggest problem they are going to experience is something called acute radiation syndrome. And this is caused by prolonged effects like an 18-month mission to Mars with high amounts of ionizing radiation. The symptoms start within like an hour of the threshold being passed, and these can last for many months. The early symptoms are usually nausea, vomiting, and a loss of appetite, all of which not only make the experience of the astronauts much worse and reduces their overall health, but can also be a general risk based on the time that the astronauts start experiencing this radiation sickness. Water filtration is also another major problem that we found. The solubility of the ice on Mars, there's very little pure ice on Mars. There's organic compounds, it's mixed in regolith, and there's a lot of different types of salts already soluble on the ground. So if you just dig it out of the ground and don't apply any sort of water filtration system like all the teams listed there haven't, then you're going to run into some major issues with your astronauts trying to drink salt water and all those things when you use this ice and extract it out of the ground directly to use for things like food and drinking water. Staying on the idea of plants, we also found that a lot of the teams did not actually specify where they were getting their nutrients from. There are plenty of resources, there are plenty of sources on Mars that you can use to get all the nutrients you need for plants, most notably nitrogen. But going through all the reports and stuff, nobody really specified where they're getting it from. And one team did do it. They said they're going to bring all their nitrogen from Earth. And our response to that is, what happens if something happens with the nitrogen, like it gets contaminated, you lose some of it, you need to produce extra food. Now you're stuck in a spot where you're not able to overproduce it when needed, and you're just not going to be able to do anything there. Sticking with the idea of food again, we have menu fatigue. Although this doesn't seem like a big problem at first, just the astronauts getting bored of the food, whatever. This has a very big psychological impact on the astronauts over time as it wears down their dopamine level. This is going to lead to a loss of appetites, which of course that's going to lead to the astronauts not eating enough food, losing body mass, and getting nutritional deficiencies. And this will make the astronauts less efficient and also start causing some serious mental issues over time, which are all going to sort of compile up onto these astronauts and make not only their experience on Mars worse, but make the whole world question why we sent these astronauts in such horrible conditions in the first place. So now the rest of my teammates are going to go forward and explain some of the other issues we found more specifically for each team.
Yeah, I think I'll ask Brian to speak about what's next.
One of the main issues we found with the Polemos team, Team 3, is that with the nuclear reactors, should there be an issue with one similar to the SL1 reactor in the 60s, which ended up killing 3 individuals, should there be any fatal errors with that, do you have I was curious if you had any protocols in place or storage that could survive the 6-month maximum period in order to wait for an abort. And I also found alongside that issue is the drilling. As you're heavily reliant on melting the ice and pumping it, do you have any protocols in place should the drill seize up, should the water freeze inside the drill, or should the drill simply get stuck? And another main issue we found was the lack of a filtration system. As Vibhav stated earlier, there could be many contaminants within the ice that we think could be damaging. And as you said in your report, it's possible that there could be life within the ice that we do not want to introduce to the team. And also the lack of exercise and decompression sickness possibilities that could occur can be damaging to the crew and could lead to death if not handled correctly, especially considering that the majority of the atmosphere in your spacesuits and habitation modules or housing areas are mainly nitrogen, as they're the main issue of the bends and decompression sickness.
Okay, I think we can move on to the next team. Carl, would you like to go?
Oh, can I add to the Polemos one? Okay, so your team chose the Milankovitch crater as a landing site, correct? So the landing site is one of the first considerations in a manned Mars mission, but there's already a misstep here, I believe. So you explicitly wrote in your paper that assuming the crew cannot find a way out of Milankovitch crater, they will have approximately 11,000 square kilometers of Martian land to explore in only 550 days. So to allow for a more in-depth study of the most scientifically interesting areas, the astronauts will spend 2 to 3 months investigating each of the 6 areas of the crater instead of trying to explore every square centimeter of the crater floor. So the first problem here is you don't have a way out of the crater. And relocation wouldn't even be an option if the conditions on your landing site become unlivable throughout the extreme seasonal climate of Mars. So you're enclosing the astronauts in a trap from which they cannot escape in a life and death situation. So, but this is not the only problem. So by making the astronauts do the dirty work of exploring just this one piece of land is kind of not worthy of an entire crew of a manned Mars mission. So if what you want is to examine 6 patches of land, right? So then a team of rovers can easily do this. And in addition, what's the point of studying just one crater? So for sure, one crater is not worth an entire crew of astronauts exploring for months straight. So in order to understand Mars better, what we need is breadth of data from different areas of the planet. But unfortunately, not one of the data that you will collect will be generalizable to the planet as a whole. So if you found out that the Milankovitch crater is not suitable for living, then the mission has no direction but go to waste. So this is not a risk worth taking for a huge investment like a manned mission to Mars. So even if the crater is interesting, what then? It's not like every future manned mission will follow you to the Milankovitch crater, as you have been claiming in page number 5, where you said that future missions will likely land in your area. But depending on the big if that the crater is promising. So even if it is promising, you have no way of knowing that it's indeed more promising than others because you've limited yourselves to one crater only.
Okay. Yeah. Do you want to continue for team 5?
Okay, team 5, a mission that I don't believe doesn't have a name, but from what I read, one of your objectives is collecting samples for geology and planetary science. But the drone you will be using doesn't sound very plausible for this. So on page 11, you mentioned that the drone possesses a small drill to collect samples in unreachable locations. So yes, the idea sounds good, but it's missing one important thing, the design, the word that it's in the name of this design class. So anyway, point being, you don't have a design for the drones and not even a reference of it. So there is no strong justification for the presence of drones, which will be nothing but additional weight to the overall mission. So the unreachable locations are also not specified, and you have not elaborated on
what makes the samples in these sites even worthy of being collected? So the drones is nothing but a decoration on the mission paper if there is no clear objective on what they should be looking for. And a little after the section about the drones, we went to your concept, not design, of the balloon. So your paper said in page number 12 that, and I quote, "The camera on the balloon will help obstacle avoidance. However, there is no plausible mechanism on how the balloon will avoid the said obstacles. And the balloon is at the mercy of the winds. And what you say is simply an empty promise, especially without the design you're proposing. So this has the exact same problem as the drone. Where is the design? So the fact that you didn't consider the weight of the instruments and even how you will inflate the balloon seems very hasty for a huge undertaking like a manned mission on Mars. And in addition, the drop zones, the things you'll drop from the balloon to study dust devils, is very invasive to the Martian environment. And the balloon New Era using in our mission uses hyperspectral remote sensing. And in contrast, you are littering on Mars without considering how much you're going to clean up the mess you will bring. And not to mention that you're planning to dispense stuff you wouldn't be needing anymore. To quote your page number 12 again, paragraph 1, the balloon are also capable of landing payloads such as instruments, which wouldn't be of use in this mission. So if you're talking about the potential mission on Mars in the future, like the potential mission that will follow your mission, then you're dwindling that chance down by scattering pieces of trash and metal everywhere. And this would make ground navigation for rovers or trucks more difficult. And so using drop zones and dispensing instruments whenever you want without considering the ethics and the action plan to retrieve your trash is a very irresponsible thing to do in the long run. And we often say that Mars can be another place for humans to live in, but you're already ruining it early in the game.
Okay. Vasti, do you want to go?
Sorry, yes. Can you go to the next slide, Maya, please? Oh, sorry, Arya. Yes, so for team one, I guess the first 2 points have been discussed in the general discussion anyway, so I'll move on to the third point. We noticed that you had elected to bring an explosive, so we were wondering what exactly is that and why do you not consider to manufacture it on site, as we do believe that this is possible. And you did mention that the crew will be eating algae throughout the duration of the mission. And so, again, we were wondering about how will you prevent menu fatigue, as they will be eating the same thing for the whole duration of the mission. And you also mentioned that as an option to give them a little more variety, you may have fish from your aquaponics farm, I believe. So we were just also wondering, how will you make sure that the fish is properly cooked, and how will you dispose of any waste that is generated from these fish, either consuming them or just through the natural life cycle of having an animal farm. And for your spacesuits and EVAs, you're electing to have an exoskeleton. So we were worried that if you're adding this to the initial weight of the suit and life support system, 50 kilograms is quite a heavy weight to be carting around when an astronaut is carrying out activities on the surface of Mars. So yeah, if anyone has anything more to add for this slide.
Can I add something for team one, but not necessarily on the slide? Okay, so team one, the Valles Marineris exploration mission, I believe. So in page number 4, your report indicated that one of your first objectives is seismic sensors and explosives. So this is where you said that mission scientists will install a number of seismic sensors and choose as professional geologists the most promising sites. That's a quote. And however, there are no promising sites proposed in which your astronauts will install the seismic sensors. So you yourselves wrote that the astronauts need to maximize their stay on Mars. So how come that you don't have a concrete idea of where to place these seismic sensors. So to quote your paper on page number 8, a manned mission should not waste time on tasks that robotic missions or satellites could do also. So the astronauts cannot just begin exploring promising sites once they're already on Mars. So it is our job as mission proponents to give them a vision beforehand and a plan for how and where this research will take place. But however, your team doesn't have the exact locations or even a slight gist of them on where these seismic sensors will be installed. So in fact, you have this very same problem on page number 3. You said, and I quote again, that you will observe water-atmospheric interactions while looking for potential for larger subterranean water bodies. But the problem is you can't keep making big promises like this while not supporting them with facts and evidence. So your mission loses credibility if there are such huge conceptual gaps like this. So besides, your choice of landing site does not align with this objective at all. You chose Valles Marineris, right? So which is located at 14 degrees south latitude. Now we all know that you wouldn't be able to expect water even underground in such low latitudes. We learned this in one of our lectures about the swim mission that discusses the consistency of water and ice on Mars. So maybe you have the time to rewatch that lecture later. Besides, even if you did find ice or water on higher latitudes, how do you expect to get there? It's not like you have any long distance vehicles as well in your mission, aside from a rover that can only last 14 sols, as mentioned in your page number 15. 14 sols is way insufficient to travel long distances in a small rover, extract water, and carry it back to your base. It seems to me that the different pieces of your mission do not fit very well together, and your objectives don't align with the landing site, and now your plans don't align with your transportation action plans. And so this mission, I think, is not as well thought out as I would expect it to be. And I would love to hear how you're going to address these gaping inconsistencies.
Okay, I'm going to speak about Team 6. The first, I'm going to skip over point. The second point and fourth point are basically the same thing. I'm going to skip over that because I think we've covered it in the beginning. Something that was a concern was your caloric intake, your planned caloric intake for the astronauts was based around 2,000 calories a day. The average human burns around 1,800 calories a day just by performing their metabolic functions. And an astronaut who is going to also perform physical exercise every day will need 2,400 to 3,000 calories a day. So having an intake of around 2,000 a day is going to leave them feeling a little undernourished, and their performance is going to decrease drastically over a period of time such as 1.5 years. This also adds to the lack of an exercise schedule, which we weren't sure about from your report. And lastly, the rover that you mentioned was part of your mission was for human use, but I think was unpressurized. So we were wondering on how you plan on this working, and whether you would have to have it pressurized or not if there are humans in it. Yeah, I think that's it, unless anyone wants to say anything else about any other team that we missed.
Yeah, I have something to say about team number 6 as well. So I would like to talk about your mission objectives. So one of the central parts of your mission is algae. And in page 3, you wrote that you will be observing how the algae does in the Martian atmosphere. And I quote, "While we're sure that it will survive, whether or not it truly thrives or not is not yet known." So again, there's no strong justification for this. So a hypothesis would be nice, but there aren't any predictions on what you expect to see while growing algae on Mars. So, and besides, there's no concrete plan as well in growing it. So you haven't listed anything about your technological capabilities, but why is it that, but why is that when your entire mission depends on these algae? And you're even basing the nutrition of the astronauts on your algae without any long-term backup plans. If the algae doesn't work, the mission is dead. So however, if the algae does float, the mission would be dead too. So growing algae will be an irresponsible contamination of Mars, and you don't have anything to contain the growth of algae. So in doing so, you might even be ruining our chances of even finding the genuine life on Mars, because you would have already introduced Earth's biodiversity to it. So you yourself wrote on page number 3 that you're sure that algae will survive, but you do not know if they'll thrive. So if they do thrive, then the fact that you don't have any contingency plans makes your mission very destructive to future research on Mars. So you don't have any contingency plans when the algae's growth becomes uncontrollable. So planning to grow algae on Mars without an idea of how you'll exactly grow and contain them is irresponsible, to say the least, and also short-sighted, considering that the survival of your mission depends upon this one thing, and there are no backup plans when it fails.
Okay. I think that's it for us. We'd also like to say thank you to all the other teams, because we got to read your reports, and we look forward to discussing your responses tomorrow, as well as putting across ours. Thank you.
Okay, thank you, team 2. So you were you guys went for about 20 minutes there, just FYI. Okay, next is team 5. Team 5, are you guys ready?
Yes, I believe we are.
Okay, you have 30 minutes.
All right, I'll start. I have a few questions for team 1. My first one would be, what kinds of insects are you cultivating on Mars, and how are they going to be contained? Because it's extremely risky to bring live animals on a mission, especially small creatures that are capable of quickly multiplying. So if they escape their container, they can spread all over the Hab, and that could ruin the mission if they get out of hand. And adding on to live animals, how do you know that your fish can survive in Martian gravity? You don't specify what kind of fish that your mission is bringing, but a couple of years ago, the ISS tried to study Medaka fish in space, and they all lost bone density almost immediately after entering orbit, and it only survived for a few months. And in general, specifying the species of fish that you will be bringing to Mars is as important information, as different varieties can require like freshwater, saltwater, different pH levels, a different cubic area of the water tanks, and a kind of food and chemicals needed to keep them alive in an artificial environment. So does anybody else have any questions for team 1 on my team?
Team 1, you mentioned using temporary solar power while getting the mission started up. But how do you know that your solar arrays will produce enough power because of the strength of the Martian sunlight? And also, what do you do if your solar panels get covered in dust? Will you have your astronauts clean them off, or will you have the process completely automated?
I guess I'll start my questions for team 3. So in team 3, you mentioned that in your report that nitrogen will be extracted from the atmosphere by condensation process, which your reference states is one of the steps of an atmospheric processor system that would separate each gas by liquefying it. Now, methods of air separation by condensation are not only a very energy-consuming process, but require a huge amount of your payload, as the same process of cryogenically separating gases on Earth requires like huge industrial towers that by itself would overcome your mission payload limit. So are you expecting by 2030 that somehow a giant industrial tower will be shrunken down enough to fit in your payload? You also mentioned that in your spacesuit, you will use a modified version of the Z series spacesuit design as your spacesuit.
the most current Z-series spacesuit, the Z2, is expected to weigh around 143 pounds in total. They significantly cut that size down to only 80 pounds. So do you have any specific details of what these modifications will be, or completely depending on assuming that in 10 years of technological development, the Z-series spacesuit will be able to function on Mars and weigh only 80 pounds? There's also the fact there has been no recent news of any developments in a Z-series spacesuit in the past couple of years, and currently NASA is focusing more on the X-EMU spacesuit instead. Does anyone else on my team have any questions for team 3? All right, then I'll just start with my questions for team 6. Team 6, you don't mention any way of getting nitrogen for your crew. The Earth's atmosphere is roughly made of 78% nitrogen and 20% oxygen, but the remaining being other gases. You do describe in your report a way of getting oxygen, but humans cannot breathe pure oxygen for longer than 24 hours without serious lung damage and other medical complications. So that's something that needs to be fixed in order to have a successful mission. Also, one of your scientific objectives is searching for fossils. One of your crew members are said to be trained to identify and properly excavate these fossils. You do have a geologist and biologist, but it's not mentioned that they have the training to conduct that sort of research. You also don't mention any scientific instruments that will be used to search for fossils. So I'm assuming this task is done manually by the astronauts. And your report also doesn't describe any systematic method in place to systematically search for these fossils. So is the crew going to go around and examine each square meter of land one by one? And how much time is dedicated to searching for these fossils when it could be spent on something else that has a higher chance of successfully finding life on Mars? My last question is, does Niger Vallis have deposits of water, or is this ice water generally spread out and saturated into the soil? Because you mentioned in your location section that you would use ice coring to collect water. So you have a specific idea of how this ice water would be transported to the distiller, such as using a rover, or do you have an estimate of how many trips the Marsnauts may need to take in order to collect enough water? Because if it takes a long time to get wherever you're needed to collect, wherever you're going to collect your water, or returning that to the distiller you're using, that process would take up a significant amount of time and power and the crew's energy, if the amount of ice coring that your drill is capable of doing is like a really small amount. So you have to like manually one by one bring ice cores back to your distiller that you're using.
I also have a question for Team 6. With your algae farm, you mentioned that you would be possibly modifying the algae to provide more nutrients for your astronauts, but you never directly mention how you're going to be modifying your algae. And so I was wondering, what processes specifically have you looked into that would modify algae to become a main source of nutrients in somebody's diet?
Does anybody else on my team have any other questions they want to ask?
Okay, are you guys done then? Last call for Team 5. Any criticisms? Okay. All right, well, we'll move on then. Okay, team 6 is next. Team 6, are you guys ready? By the way, team 5 used about 8 minutes. Team 6, are you guys ready? Anyone from team 6 here? I don't actually see anyone. Okay, I guess we're gonna move to team 3. Team 3, are you guys ready to present?
We are. We're just waiting on some of our people to come in to get ready.
Okay.
And there
So
I am.
team 3, you guys will have 30 minutes, and then we'll go back. We'll probably do team 1 after you guys, and then we'll go back to team 6. I'll try to see if they can get on the call. So go ahead, you guys have 30 minutes, team 3.
All right, Max.
Yeah, sure. So a lot of, I believe it's team 1 and 2, they mentioned mission critical 3D printing. So I've read a lot of papers and they all say that 3D printing is unlikely to be viable for mission launching in the early 2030s. And then another common theme was solar panels. And a lot of teams estimated that that there would be 40% efficiency. But from what I've read, it's actually 20 to 30%, and this is unlikely to go up.
Additionally, teams 1, 2, and 6 all have designated mission doctors. And I believe this is a point that Robert Zubrin himself was against. Definitely Roald Amundsen, the guy who he quoted in The Case for Mars, was against it. And what Roald Amundsen said was, A, nobody likes doctors. B, morale's going to go down. And C, a lot of the medical emergencies that occur on these missions can be handled just as well by the explorers. So for that reason, I'm not exactly sure a designated doctor is necessary. And then, Max, I believe you had a bone to pick about the 3D printers.
Sorry, what?
I can also go if that works for you guys. Not hearing any votes for no. So team 1, I noticed in your paper that you plan to have, I believe, two modified versions of the Raymer Mars plane. That doesn't really seem feasible to me for a first mission to Mars, because you say you're going to reduce its size by 30%, but even once you've done that, it will have a 63-meter wingspan, which is way too large for the 8-meter diameter landers we were told to account for. And then additionally, the payload numbers don't really seem to make sense. You say it's 30% smaller than Raymer's plane, but it's meant to carry more than twice the payload, 500 kilograms versus 226 kilograms from as the payload for the larger version. 8 times the distance. It seems like it's a bit of a stretch to try and develop something that capable in only 10 years. I didn't have the time to design a whole plane, so I can't say it's impossible, but it doesn't seem feasible.
And
I have a couple other things. And then at its top speed of 300 kilometers an hour, its 4,000 kilometer round trip would take 13 hours, which seems quite a long time to be in an EVA suit, especially since your biosuits don't have any food or water supplies. Additionally, are you planning to have those suits be capable of surviving 300 kilometer an hour impact with terrain if autopilot fails or the human pilot dozes off from fatigue during that trip? I believe the DMV on Earth recommends that you only drive for 8 hours a day, and cars can't even get up to 300 kilometers an hour. And lastly, your passenger rover seems to be 10 meters long. I think there's the same issue with the size of the lander there. Still not sure how it would fit, but I'd love to know, because if you're using space compressing technology to get it to Mars, I can tell you that Team 3 would really love that for our rover too. Would mean we could fit it all on one descent stage. And then you seem to use inflatable tires, which haven't been tested on Mars, and it doesn't sound like you're going to have spares, according to your papers, but maybe you just left that out. All right, Peyton, Maximus, Nicole,
yeah, so
back to someone.
on Team 1 as well, I noticed that you were using a microwave system to collect water. And I looked at the sources, and it's not a bad idea. There's a lot of sources that agree with you that this is a really good idea. Now, the problem is with the landing site, because I have the red water paper up right now, and it includes a map from the Special Region Science Analysis Group. And Valles Marineris is in Unit 4, possibility of transient surface water inferred from recurring slope lineae. So is there really going to be enough ice underneath the regolith or in the regolith to be able to let this happen? I'm not entirely sure. And I'm not sure what data you might have on the matter.
Team number 6 mentioned that they're going to be using a 50 kilowatt kilopower reactor, but this is extremely off. Currently, the only kilopower Krusty only generates 1 kilowatt, and by 2030, NASA thinks they can only get it up to 10 kilowatts. I haven't found a single source that says by 2030, a 50 kilowatt reactor will exist.
As well for Team 6, there are only 3 things that you're really going to be eating on Mars: MREs, potatoes, and multivitamins. Sounds a lot like the Martian, but that's besides the point. The problem is that potatoes use a lot of area. And I'm going to keep going back to the Martian for this because there is a lot of great science in there. He used the entire space of his Hab for that, and admitted that his farming wasn't sustainable. And I'm paraphrasing a little, but he said that this would turn a farmer's farm into a Dust Bowl within 5 or 10 years. It's not sustainable. Maybe it would be all right for 1.5 years, but it's not sustainable, and there's a massive amount of space you need to feed everybody with 4.5 baked potatoes per day.
All right. If no one else wants to go right this second, I have a couple comments about Team 5. So, first of all, you seem to think that an advanced Stirling radioisotope generator will be able to power your 40-mile-per-hour crewed rover, but that doesn't seem possible because the ASRG, as it exists right now, produces 130 watts of power, which really isn't enough. I'm not sure that could even run the heaters, but that's beside the point. Additionally, I'm a little confused about why you chose to stay for less than a full transfer window, meaning, sorry, 1.5 years on the surface, just because you have the option to stay for longer, and you could do more. You could do more science if they stayed another 6 months. And then lastly, I'm wondering what the astronauts in the buggy will do if they, for example, come over a Martian ridge and hit a rock anywhere near their top speed. I'm wondering, are there going to be seat belts? Do you know if a crash at that speed is going to damage their suit's life support systems? Is it just going to completely ruin the buggy? And if so, does that mean your fastest vehicle is significantly limited in speed so it doesn't hit stuff and that doesn't happen? Or limited in range so that the astronauts can walk all the way back to the Hab? Please elaborate on this.
Team number 1 is planning on using explosives, which seems just crazy on Mars. Both of the chemicals they're using are extremely flammable, so the whole Hab would basically go on fire. It's probably not a very good idea. Would not be good for the astronauts. So I'm not sure why we even need explosives in the first place. No other team is making explosives on Mars. It just seems very unnecessary and very risky.
Okay, do you have anything else?
We do, just give us a second. There we go. So on Team 5, they mentioned, actually, sorry, no. Where was it?
Here, for team number 1, they also mentioned their mission is 50 months long, I believe, not 18 like the maximum limit is. So I don't know what to say really to that. We had a limit, so they kind of went over that.
All right, so for Team 2 in section 3.2.6 communication, they mentioned that they were going to have beacons required for the ham radios placed in the pressurized truck in the Hab, allowing the crew to have a portable beacon as well as a stationary one, which each having a radius of about 150 to 200 meters. And here things get a little confusing. what has the radius? Is it the suit radios? Is it the beacons? I don't know, because ham radios on Earth have a range of 2 to 36 miles, which we can expect to only increase on Mars because of less atmospheric scattering. There is basically no atmosphere. And so I am confused. That number seems very low, and I'm not sure why one would intentionally restrict it, but I'm also unsure if this means the beacons or the radios. In which case the beacons would be a problem, because 150 to 200 meters, if you try to go on any significant journey on the rover, then you lose radio contact with the Hab, and that is a big problem.
Team 6, I know we're jumping around here, so sorry to anyone who's trying to take notes. But I'm wondering about your science strategy, because during your presentation, you said you would go to Mars, collect a bunch of data, and then analyze that on the way home, which seems like an interesting use of your time during the Mars to Earth transit. But it also seems like you won't be able to redirect your search to the most promising areas if you don't turn up anything in half of your mission, your operational area, and then pass over a smaller area where you find a sample later that indicates it's promising because you were only scheduled to take one sample there. Anyway, please elaborate on why that strategy is better than analyzing it on the surface and using that information to direct future EVAs and rover operations.
I think that's it, right?
I do believe that is it.
Did we mention aeroponics?
I don't believe we have. If you want to go ahead on that.
Oh, yeah. I just noticed that for team member 5, we noticed you are using aeroponics to produce fuel, which we didn't go for in our paper because it seems unnecessarily complicated since you have to disassemble the entire thing and clean it to prevent clogs pretty frequently. That seems like a waste of manpower. So could you explain why you went with that, please?
Well, I mean, we aren't looking for a defense right now, but that'll be something for round 3.
Okay, are you guys, do you have any other criticisms?
Not unless Sebastian pulls something out of his hat again. Thank you, guys.
No, I think my hat's empty.
Great. All right, you guys won about 21 minutes, just FYI. Thank you so much. Okay, next is team 1. Team 1, are you guys ready?
Yeah, we're ready.
Okay, awesome. You have 30 minutes.
All right, let me just share my screen, my video. So we presented a PowerPoint with all the different questions to the other teams. So first, the questions for team 2, for the science part. For the scientific targets, is it really worth to have a manned mission for these targets, as they're quite easily done by robots or rovers that we can just send with another rocket without a Mars mission? Then can most of your objects be done by unmanned missions, exactly, or on Moon or in a space station in orbit, like the solar panels, for example, could be also done on the Moon. With the Moon is has different is of course cheaper than having a mission sent to the to Mars. And why do you want to use an unmanned balloon on a manned mission? Because it seems like you arrive to the to Mars to only set up a balloon and a rover, and then you kind of have some free time with the astronauts. Then some controversial numbers we found for the energy production and usage, of course. Then your methane generation has 25 kilowatt capacity, but you wrote that your habitat requires 75 to 90 kilowatts. This could also be a mistake, but we're quite curious on that. And we would like to have more information on the primary energy supply and the weight of that. So next, the habitat is constructed by robots in Team 2, and they want to have a regolith layer to protect them from radiation. Now, our question is, how do you glue the regolith together, and where does the glue come from? Because just regular sand and dust doesn't stick together that well. Then the mining robots. Why is it so heavy, and how does it operate without humans? I would think that the mining robot must be quite accurate to not destroy any of the habitats or maybe even destroy itself. So how would you do that? And the crew selection. Why so young people, and what about the experience and radiation consequences? That is, we are concerned that if you bring so many young people on Mars, I think your youngest could be 28, that they have limited education and also have a higher risk of radiation sicknesses or diagnosis back on Earth. Then your number one has, which is I think an engineer, has too many functions, which is a psychologist, mechanic, a chemist, and a pilot. And how do you think that people have so many qualifications, and with your info that they could be 28 years old to 40, how would they have this much knowledge while still being almost fresh out of school? Then the space ready suit, like other teams said, the 2-meter range is oddly short, and this might impact the mission safety or even just data conversion. Then using the lander as in okay, these are so we're finished with questions for team 3, and now for team 2, sorry, and now the questions for team 3. Using the lander as an internet habitat while building a bigger one, we're not sure if the competition allows for something like that, and if we would have a Starship landing on Mars as a habitat, we would plan our own mission entirely different, of course. Then your habitat is 16 tons, which is more than half of the mission weight. and we would like a rough list on the weights of all your essential items, reactors, food supplies, and so on. Then water gathering, you have a plan where you use a 5 kilowatt nuclear reactor on a rover, and is it strong enough to melt ice? And how do you prevent water not to freeze as it is pumped back to the rover, as the outside temperatures could be way under a freezing point and just not work anymore? Then your water extraction methods assume extremely pure water layers to melt. What if you cannot find subterranean ice layers? Then power production for team 3. You claim that you need 10 to 20 kilowatts for life support per person. That is on page 13. And that would normally amount to 50 to 100 kilowatts for all crew, only for life support. You have 2 kilowatt reactors, and that doesn't seem to add up for me. I'm just curious how that works. Then you're quoting a 40 kilowatt from NASA for a Martian base. How do you know that your base is same as NASA's base? Maybe look for different things that you maybe overlooked while planning your base. Then we would like to have your power consumption breakdown and the complete mass breakdown, as 16 tons for a base would be. Then for other resources, the mass should be quite thin, or it should be quite light for it to fit it all in the rocket. Then that is it for team 3. And now for team 5. For your science, your main object is to study effects on human health. For the first and potentially the only mission to Mars, is that really the most important field of science and reason to come to Mars? And could balloons be deployed by unmanned missions? That is, so we have the same question as for team 2. Then the drilling. Do you assume that 10-meter drilling down is sufficient? And if so, why? So we think that only 10-meter drilling does almost nothing for science. Of course, it does a lot, but if you would have more range for drilling, it would be way better for the mission. Then the water. Your 5 kilowatt nuclear reactor, is it on the rover? Is it strong enough to melt ice? We would like to receive some calculations about that, maybe some sources. Then how do you prevent the water not to freeze? Okay, so we have the same questions as for the team 3. How do you prevent the water not to freeze as it pumped back to the rover? And your water extraction methods assume entirely pure water layers to melt. What if you can't find ice under the layers? Then 3D printing. How do you get resources for printing from mining on Mars? And how about human resources? So you only have 2 crew members in the Scientology. Oh, you have 2 crew members that are a scientist and an astrobiologist, and then you have 2 crew members that are pilots and botanists, who will do geologic research to find traces of life. And what happens if someone gets seriously ill, as you don't have any kind of doctor or anything else? Your main task is to observe human conditions on Mars. And do you have any specialist for the signs, like, for example, a doctor? Then your mission weight. Your habitat is 12 tons. is it so heavy because of radiation shielding? We'd like to answer for that. And you only have 5 kilograms of plastic spare parts. Our question is that enough for the whole mission? Then you bring 800 kilograms of sport equipment, and this seems like a lot for me, and maybe it was a miscalculation or some type of error. And why would you not just let the astronauts work more physically? And a 1.8 kilogram Sabatier reactor, will it be sufficient to produce methane for the return flight, as you said in your presentation and your paper? Then what do you do in a case of failure with the water extraction equipment or after bad harvest? Your astronauts will have no way to survive or any extra rations for emergencies. And also your astronauts might get some kind of radiation disease with the exposure of 300 MSV per year without any radiation protection. That's it. Thank you. So thank you for all the teams. Thank you for the papers. That's it. Maybe other team members want to also say something if they want to. Many don't have time, but if they want to, that's also great.
If I may, could we have a copy of the slideshow or an image of some of the slides that criticize Team 2? As we would very, very appreciate that.
Oh yeah, that would be great if you could send that on email or any other source.
Okay. Thank you.
Thank you very much.
Okay, thank you. Thank you, Team 1. So you guys went for 13 minutes. All right, last but not least, Team 6.
Hi, can you hear me?
Yes.
Okay, so for Team 1, the main things we found were, first off, you had one doctor on your team, and while it's great to have medical abilities available, it wasn't, you didn't say like, I think it was just a lower amount, and you didn't, like, if something were to happen to that person, if they weren't able to treat themselves, then you'd be out of luck and possibly in danger. Another thing is that you guys, you don't have, I know chemistry wasn't a major point, but it was enough that you would need some decent equipment to do your research. But all you really have are basic materials like beakers and then a X-ray diffractor, I believe. But my question is diffractometer. No, yeah. Is that going to be enough for all of the chemistry that you want to get? Okay. Team 2, so main things we found, first off, something that's been said a couple times already, is the 200-meter radius is an incredibly short amount. And if something is to happen outside of that radius, then you could lose members, lose efficiency, anything like that. Also, just a more minor thing on your Hab, I believe you're wasting a bit of mass with your with some of the passageways that you've got, because it's pretty long passageways that don't seem to have too much purpose, at least that we know of. Team 3, so you guys have very heavy suits, and I believe some of your crew may be able to to carry those, but with the exoskeletons combined with the slightly bulky suit, it'd be a lot for lesser strength crew members to carry around. Also, you don't have too much of an exercise system. I believe you have a couple equipment, but it may not, is that going to be enough for their team? Also, the water filtration system isn't great. And Team 5, we've got a few here. So the first one is we don't see any materials stated for much of the Hab, or at least the greenhouse. And if that could change your weight of the mission quite a bit. Also, you're going to have
Bro, you're muted. You.
Jaden, you're muted now.
Oh, sorry. Okay. You're going to have laser communications, which our question for that is, how are you going to deal with light diffusion? We could not find any, or we did not see any methane storage, and we did see that you were going to be getting some. So also, you're going to have a 3D printer for spare parts, I believe, but you don't state how you're going to get the materials from the regolith, and also there's no mining or processing mentioned. The RTG is not enough to power your rover, because it produces 260 watts, and most vehicles will use up to 8 kilowatts at that speed. And also, we did not see any materials stated for said rover. And I believe that's it.
That's all your criticisms, Team 6?
Yep.
Okay. So you guys spent about 5 minutes. Okay. All right. Well, that was all the teams. Yeah, those were good criticisms. Go ahead, Robert. Do you have a comment?
All right. First of all, just a question to the gentleman from Team 6. You got muted a bit, and it was unclear where you were criticizing Team 3. You criticized their EVA suits, their limited exercise equipment, water filtration system. And then you also made criticisms of laser communications, methane storage, and 3D printing, and a Stirling-powered rover. Were some of those criticisms directed against Team 5? Which were directed against Team 3, and which were directed against Team 5? Because you got muted in the middle and it was unclear.
I'm sorry, I believe the last 3 or 4 were based against Team 5.
Okay, thank you. All right, so with that clarification, so tomorrow you guys want to answer all the criticisms made against you. Now, if you have extra time, in other words, you've got a half hour, and if it takes you less than half hour to answer the criticisms, you're welcome to use your remaining time in your half hour to summarize why your design is the best, that we have the best site, that we have the right equipment for the site, we've got the best science program, what we're doing is proven technology. In other words, you can use it to basically getting off the stage punch. But don't use it to make criticisms of others. You've made that today.
So answer the criticism view, and then you can summarize the strengths of your design. You know, it's the one with the most reliable power supply. It's the this and that. It's the one with the most backups. Does the most science. It's, you know, so forth. In order just, you know, give. So you should be sure. You know, you need to work this out. So who's going to answer the criticisms, and you probably and then who's going to deliver your final getting off the stage message. Okay, drive the points home. All right, so this is very interesting. You guys got some homework to do to back up your designs. Some of the criticisms that I heard today are quite valid. Some are actually not true. But you've got to show us. So good luck. See you tomorrow.
Okay, everyone.
Thank you.
And by the way, one more thing. We're going to want to produce a book of your final designs. Now, in the case where they really have scored you on, you know, or they did find a weakness, on your final design report, you can correct that. Okay, so you can take your basic design and revise it to, you know, in other words, in engineering design, ultimately it's got to work, and so it's not personal. I mean, it's personal now while you're competing for the judges who has the best mission, but even the best mission is subject to improvement. So you'll want to do that. Also, after all the things are done, the judges will have a chance to offer comments for it. So, Jim, do we want to schedule a fourth day for the judges to, in other words, to get everybody together, and the judges can tell people who won, and, you know, and maybe one of the teams didn't win, but it had the best science program or the best, you know, best in some other category.
All right, thank you so much. We'll see you tomorrow. All right, good morning, everyone. Welcome to round 3 of the Mission to Mars Design Challenge. We're really excited. Today's the last day, and you're going to give your rebuttals to the criticisms you received yesterday. So we're going to go basically in numerical order today. We're going to start with Team 1. So Europe and Middle East team. So you guys have 30 minutes. Are you ready to present?
So the landing site is not relevant for our scientific goals. This argument is just not true. Valles Marineris is one of the most interesting geological structures in the solar system. It is one of the most promising sites for finding past and present life, as well as studying the geology of Mars. Then there's no water in low latitudes. Then please check our sources, because we found that there's 40% water content within the first meter of soil in Kandor-Kazma. Even if this turns out not to be the case and the water content will be average, our extraction equipment would still manage to extract the needed amount of water. Then the water transport with Rover is not feasible. We don't plan to do that. The water will be transported in vapor form to the base via pipes. That might be a mistake from the other teams, because we don't plan to use the rover for water extraction or water transportation at all. Then no water filters. We use magnetrons. So we have water filters in the condensation plant just in case, But since we are evaporating the water and then condensing it, it's distilled and should be clear from any impurities whatsoever. Then no plan for seismic experiments. The seismic research is an important part of our mission, but right now humanity doesn't know pretty much anything about seismology of Mars. That's why it's impossible to choose the seismic experiments sites right now. The selection will be done by our geologists once they're on Mars and have completed the initial surveys. Then explosives are too dangerous or make no sense at all. Saying that something makes no sense is a wrong mindset to us. We're trying to be as innovative as we can. We have chosen a water peroxide ethanol mixture for explosives since it's very easy to produce on Mars. And we're producing it on site and using it up as we go, since hydrogen peroxide has a tendency to quickly decompose. We will use those explosives to produce seismic waves, which will be registered by our sensors. One team said that we're the only team to do something like that. Is it wrong that we just happen to be the only ones who have thought of this possibility? Of course not. Then radiation exposure. Our habitat will have a layer filled with water collected in situ, which will reduce the radiation inside the dome to below Earth levels. Our rovers and ETA suits will have basic lightweight radiation shielding sufficient to prevent deadly doses. The base crew and the expedition crew will swap from time to time in order to balance out the radiation doses which they receive. Solar panels are not 40% effective. And how to clean photovoltaic. We have provided the sources for the efficiency in our report, since this type of solar panels will be used only when the astronauts are present. One of the crew members will brush away the dust from time to time with a long brush. Then exoskeletons are too heavy for astronauts. The exoskeletons can be taken off when unnecessary, thus allowing our astronauts to enjoy the mobility of our mechanical counterpressure suits. When an astronaut is using the exoskeleton, they won't feel its weight since the exoskeleton supports themselves on their own power. Then counterpressure suits can cause decompression sickness. Decompression sickness is caused by rapid change of pressure. Our suits provide constant mechanical pressure to the skin, with the exception of the helmet, which is filled with air. There will be no rapid change in pressure at any moment, so decompression sickness is out of the question. If the suit ruptures, the pressure force is lost, and only in the place of the rupture and not everywhere. Airplane is too big for rocket launch. Rover is too big for the same rocket launch. The competition has a diameter limit and not a height limit for our payloads. If the rover would be placed vertically, then it fits easily in the 9-meter diameter. Same thing is for the aeroplane, although there is a possibility of transporting the wings in segments. Then how to survive an impact in 300 kilometers an hour, and how 13 hours of flight time without a cabin is too long. The aircraft are used for crew transportation only in emergencies. For example, in a life-threatening situation. There are risks associated with flying crew in the aircraft, but in case of emergencies, the possibility of fast transportation outweighs the risks. Since we're talking about emergency situations, the astronaut could take fatigue-preventing drugs in order to stay awake and concentrated. Inflatable tires not proven, no spare tires. We have provided a source for the tires in our report. We're bringing spare parts, including backup tires, since this is a manned mission, there is a possibility of them being repaired instead of replaced. How to genetically improve algae. The genetic modification of algae is already being done. There are genetically modified algae with increased fat content for biodiesel production. Therefore, we believe that in the near future, genetic modification will increase protein and carbonates as well. Algae already are a great source of nutrients. They typically contain essential amino acids, fatty acids, vitamins, and proteins. Hence, the modification process will not require extremely advanced science. Furthermore, algae is deemed to be a crucial component in our agriculture and solution for famine, meaning that the algae production industry will grow exponentially in the future. The feasibility of GM algae should not be our concern. Algae can contaminate Mars, uncontrollable plant growth on Mars, insect type. The algae will be grown as a photobioreactor, which is a completely closed system. There's no chance that the algae will overflow and contaminate Mars. Even if they overflow, algae cannot be grown without water, so contamination or uncontrollable plant growth shouldn't be a concern. If the algae were to spread and grow on Mars, congratulations, you've won the Nobel Prize. Also, if the algae is infected by any type of bacteria, there will be four separate bioreactors so that we continue the algae production in non-infected ones. Boring food, no nutritions. The food will not be boring since there are numerous possibilities to eat algae in different ways. Since we bring some dried rations, which is extremely lightweight, the astronauts will be able to use the dried algae to make sandwich, salads, or rice. We will also be bringing powdered spices, which can enhance the taste. Furthermore, there will be an option to eat some living organisms that are grown for scientific purposes from time to time. Hence, food diversity is ensured. Then missing exercise equipment. As it is said in the report, the crew members will have their own free time to dedicate to their own hobbies. With the lightweight equipment such as bands, inflatable gym balls, or 3D printed gym equipment, the members can work out on their own. But it will not be mandatory since it is crucial to mandate the use of their energy during the day. Furthermore, the doctor will closely monitor each astronaut's health, recommending any physical activities if necessary. We do not make personal exercise mandatory since we believe our mission already requires enough physical movement throughout the day. Doctors not necessary, bad for morale. Having a doctor is absolutely crucial for the success of a mission, as there is a very high likelihood of someone getting seriously ill or injured. Apart from doing whatever doctors do, there will be a scientist studying the effects of the Martian environment on humans. We will also bring a biologist with a second degree in medicine as a backup. 3D printing not viable in 2030. 3D printing is a very well established technology right now, being so common that you could go to the store and buy a 3D printer right now. 3D printing is a near vacuum. A near vacuum is not that different from normal printing, and there are plans to test this technology in the very near future. We will produce lots of plastic in situ from water and carbon dioxide. Too long of a mission. We will send our equipment 2 years in advance for reasons which are stated in our report. The astronauts will arrive later and spend 1.5 years on the surface, the maximum allowed amount. The organizers have confirmed that this is within the rules of the competition. Then what type of fish do we want to bring? What about fish waste? Fish growing is only a science experiment, and the type of fish that we will take will be decided by the people which will design the experiment. unclear questions. There were some unclear questions or invalid criticisms, some of which are listed here. Some are, why don't you consider manufacturing explosives on site? We do, we wrote it in our report. And how will we make sure the fish is properly cooked, and how will we dispose of any waste that is generated from the fish? We have a lab. There aren't many fish, and aquaponics use fish waste as nutrients. Bringing back water from far away back to base. We are landing directly on a site rich in frozen water, so we're not gonna use the rover. Temporary solar power. This is not our team because we use constant solar power as backup or an additional power source. Now, why are we special as a team? Our landing site with the best resources. Our mission will land in one of the most scientifically interesting regions of Mars. Additionally, there are easily accessible resources available, such as sunlight, water, and CO2. Base camp. Our habitat provides lots of space for living and laboratories and has excellent radiation protection. We're producing all of our critical resources such as water, oxygen, methane, and food upfront, thus eliminating the risk of critical equipment failure during the mission. Now, resource utilization. We have an extensive ISRU operating, producing water, oxygen, methane, food, syngas, explosives, and plastic in situ from Martian resources. We utilize 3D printing technologies for producing spare parts and other equipment, thus reducing the mission weight. Excellent energy management. We have 500 kilowatts of power production from solar arrays, the highest amount among all the teams. The power is used for water extraction, growing food, science experiments, and most importantly, propellant production. Our rovers and airplanes use SOFC powered by methane and oxygen as an energy source. Unique science for unique results. We want to gather answers to the most urgent and important questions. Was there life on Mars? Is there life on Mars? Can humans survive on Mars and colonize it? And we conduct outstanding geologic research, which automated missions can't do. We look for traces of life where robots can't go. And we put as many boots on the ground we can ship to Mars to fulfill all those tasks in 1.5 years. Mission equipment geared towards science. Apart from more standard science equipment, we employ unique techniques such as drills, which are able to reach 2 kilometers of the surface. We also conduct extensive seismic research with advanced instruments and man-made seismic waves. Mission equipment redundancy. Our power production uses modular solar cells and fuel cells. Methane and oxygen production uses modular fuel cells. We have multiple redundant storage tanks for oxygen, methane, and syngas. We have large water reserves in the form of the radiation shielding in the dome, about 200 tons of water. We can use the rovers as lifeboats, for example, and we employ the principle of parallel operations of rovers for fast assistance and more effective exploration. There will be a rescue system for fast evacuation in case of accidents on EVA. We have a 3D printer for spare parts, producing from plastic production in situ. We have the best team. Our team of astronauts has been carefully chosen to provide potential replacement for all important functions through double qualifications. Our astronauts are around 40 years old in order to have sufficient time to gain experiences in multiple qualifications, but are still young enough to endure physical work. We have run one professional doctor and one trained biologist to cope with accidents and sicknesses. Doctor also does scientific work. We are supported 24/7 by motivated and highly qualified ground control team, which will free up the astronauts from observing technical parameters, resource planning, and administrative tasks. Our astronauts have more time for doing science on Mars, which is very valuable. And we can be an NGO mission. We do not require plutonium or reactors. We can operate as a corporation. We can therefore make profits, and we can employ significant cost-saving measures described in detail in our report. As well, we are the only team that did some effort in trying to have something for costs, which I hope is very important. Yep, that's it. Thank you.
Okay, thank you, Team 1. All right, judges, any last questions? Okay.
No, that was brilliant. Thank you.
Okay, we'll go on to the next team. That would be Team 2. Okay, you guys have 30 minutes.
Yeah, thank you. So first we're going to be talking about the science rebuttals, and my teammate Carl will be talking about those. Go ahead, Carl.
Yes, so good day everyone. This is Team Nueva, and for this session, we are responding to all of the critiques we received yesterday. First, we want to address Team 1's question saying, cannot most of your objective be done by unmanned missions on the moon or on a space station in orbit? And the example that Team 1 gave us is our solar panels. Leonard Koch said that we can just install solar panels on the moon instead of on Mars because the moon receives more sunlight. At least that was the essence of the argument. But I think this comes from a misunderstanding of what we plan to do with the solar panels, which is totally fine. And we're here to clarify that. And we're not experimenting with the solar panels. We're using them as a secondary power source since our primary one is the Sabatier reaction. So I don't fully understand how the solar panels could be on the moon or on a space station in orbit when we're not really looking at them like experiments, but we're looking at them as a secondary power source that we can utilize on the surface of Mars. So with that in mind, there's no reason to install solar panels on the moon so we can use them on Mars unless we can transmit all those energy from the moon wirelessly all the way to Mars. So at least in the near future, our current technology would not allow us to do that. And I hope that clarifies your question about why don't we just install solar panels on the moon. So it's not a scientific objective, it's more of an engineering necessity, although it's secondary. So I'm gonna move on to talk about the other science targets, and the questions from Team 1 as well were the following. So is it really worth to have a manned mission for your science targets? And why do you want to use an unmanned balloon on a manned mission? Before anything else, let's review our objectives for a little bit, and we'll answer your question about why we need humans to execute them. So as a quick review, we have 3 main objectives: life on Mars, atmosphere and welder, and human sustainability. So the scientific objectives are the first 2 of them, life on Mars along with atmosphere and welder. So under life on Mars, the plants we will grow using hydroponics have a dual purpose. So one, they're a food source for the crew, but they're also subjects of scientific observation. We need humans for both of these purposes. First of all, we need a person who maintains the greenhouse. This is the one who makes sure that the systems associated with hydroponics technology are functioning well. And in case something goes wrong, the human is there to fix it with logic and judgment that can be beyond what the robots are programmed for. So in terms of normal functions, you may also say that a robot can replace the water autonomously and supply the nutrients autonomously. But here's a question we also have to answer.
where will the water and nutrients come from? So bringing months worth of them from Earth would be too heavy and thus impractical. Hence, we're using in situ resources from the ice and minerals present on Mars. Well, just as a side note, we're also using human waste like urine or feces that the crew will produce to maximize the remaining nutrients in them like urea, potassium, and phosphorus. So that's another reason we need humans for the greenhouse. But the biggest reason for their presence is water. We cannot sustain the greenhouse and do science on the plants without water. So for this, we're using an ice drill in Utopia Planitia, and the ice drill is mounted on a truck driven by humans. So extracting significant amounts of ice would need the human dexterity to operate the drill, and that drill wouldn't be going anywhere without a human driving it into a certain location. And this brings us to the second sub-objective, which is searching for microbial life in the ice. So in having humans operate the truck and the drill, we're not just extracting resources for our own sustainability, but we're also searching for signs of life with the help of human judgment, a judgment that will be useful in knowing when to start searching and when to stop searching. So I hope you're clear on that, on why we need humans for our first science objectives under life on Mars. So this brings me to the second objective, which is atmosphere and weather. Here you ask us, why do we want to use an unmanned balloon on a manned mission? So this is related as well to the first question, and here I will discuss the autonomous aspects of the balloon and also the aspects that would need human control or intervention. So let me reiterate that the balloon is there for two main things: detecting methane on Mars and detecting small-scale electrical discharges. So they're of particular interest because of their relative rarity, and to be able to see them more clearly means going at a lower altitude at which the satellites are currently in. So these are the autonomous parts of the balloon, and we're using three instruments: the hypercam methane, the Agile digital detector, and the kurtosis detector. We don't want a human on board the balloon because self-sustainment would be impossible. There is simply no chance that a human who needs to eat, drink, excrete waste, etc., can survive on a manned balloon, at least not with our current technological capabilities. So now we come back to the question, where do the humans come in? So in page 17 of our mission report, we wrote that in a span of 1.5 years, the balloon will be left flying until something goes wrong or it crashes totally. So in either case, a substitute balloon stored in the hab will be deployed by a member of the crew, preferably the engineer. So there will be duplicates of every instrument on the balloon for which we've accounted the cost and weight. So now the question also asks why we want a balloon on a manned mission. So well, first, it's much more convenient to deploy them with humans there, especially since inflating the balloon takes great care. So as we wrote in the paper, the rate at which inflating the balloon should be moderated so as to not damage the fabric. So the second reason for wanting a balloon on our mission is due to the sheer data that it can provide us. So because we're going to mount basic atmospheric monitors, we will be able to examine the atmosphere of Mars, not only in terms of methane and lightning, but also in terms of weather, wind speeds, the dynamics of water vapor and dust particles, etc. So the sheer range of data the balloon can give us by circumnavigating Mars is immense. So hence, having balloons on site allows the crew to gain more scientific knowledge about the Martian atmosphere with less power requirements than an orbiter and higher altitude limits than a drone. So thus the balloon gives us a better view of the Martian atmosphere while functioning with more efficiency. So this can only be done with the manned mission because setting up the balloon fabric, cables, and instrument on board, along with monitoring its status, location, and data is more efficiently achieved with a crew. So lastly, having a manned mission does not imply that everything we do has to be manned per se. Having a balloon would enable the crew to gain more scientific knowledge a lot faster. So the implication here is that the non-human and human components are working together toward a common goal, and that's what sets the New Era mission apart. Vaibhav, you're going to talk about engineering.
Yep. So for the engineering part of our mission, we got three main concerns. It was methane generation, how we're mining regolith, 3D printing, and our rover's weight. So I'm going to start off with the methane generation. I think Team 1 is the one who asked us this question. They were saying we're getting 25 kilowatt hours of energy per day from our habitation and our methane combustion, which is wrong. You can see the math that I did on the side there. It's pretty back of the napkin, so hopefully you can read it. But per week, we need 630 kilowatt hours of energy to power our whole Hab. And right now, with our current methane production producing about 17,000 moles per week, we're able to do about 2,900 kilowatt hours of energy per week as well. And this is in our worst case scenario, where a methane combustion is working at 54% efficiency, our electrolysis chamber isn't working well to the microgravity of Mars, and all those sorts of other factors that other teams haven't even considered in their water generation. So when it comes to the next part, which is the regolith creation and using that for radiation, well, Team 1 again asks us, how are we going to stick these pieces of regolith together? And our answer to that is we don't need to. There are really two main things that could potentially knock down the regolith bricks that we're going to use for radiation protection. The first one is the wind on Mars, potentially, and we've done the math on that based on the weight of our bricks and the pressure on wind speeds on Mars. There's no way that, unless there's some external outside force on top of that, that these bricks are going to fall apart by themselves. On top of that, if we have like something like a vehicle crash into the 3D regolith, well, my response to that would be, it doesn't matter if we have glue or not at that point. If something crashes into our 3D regolith wall to the point where a brick crumbles or moves, well, it doesn't matter if we have the glue or not, the wall is going to fall. So we don't actually need glue for 3D regolith there. The other thing that Team 3 said about our 3D printing was that it's not going to be viable in the 2030s. I think Team 1 did a good job of explaining why that's not true, but I'll just add another example on top. Virgin Orbit and Offset of Virgin Galactic uses 3D printers right now to print multi-materials to make parts of rocket engines, and they've been flying since 2020. So maybe at some point 5 years ago, a study came out and said 3D printers are not going to be viable on Mars, but that is not the truth anymore, and that is not going to be the reality in 10 years from now. The last question that we got on our engineering aspect is, why is our mining robot so substantially heavy, and how does it operate without humans? So the heaviest part of our robot is actually the little mining drill that we have, the 1 meter long mining drill we have at the front of it. This is sort of like the Insight lander, and it mainly weighs a lot because it's tungsten carbide, so if it chips, the whole drill does not need to be replaced. You can still keep drilling with minor reductions in efficiency. So that's the reason where a lot of the weight comes from. But on top of that, we have those 3 life detection systems that I talked about on Monday, and those weigh about 20 pounds in themselves as well. Well, our idea of bringing this rover is not so much to prevent humans from doing exploration, but to make sure they can do it efficiently. Moving humans is a difficult process. Anybody who's ever gone on like a road trip with their family definitely knows that. So we're trying to avoid this hassle of having our humans have to drive like 50 kilometers out this way and come back 50 kilometers back and forth every day for the whole mission, wasting not only fuel resources, but water and food and energy and all those sorts of things, and just have a rover go out, be like, okay, there's ice in the ground here, maybe there's life. Okay, look, what do you know? There's nothing here, but there's some interesting geologic rocks here, so I'll just collect these samples, bring them back to base, and we can do further analysis there. That being said, it's not like we can't get to whatever locations our rover is going, because with our manned truck, we do have the ability to go anywhere that our rover is going and provide and do more scientific research as we think is necessary for each instance in our mission where our rover visits. This rover is actually also solar powered, so it can be completely independent of our habitation for weeks, and it is remotely controlled, not completely independent in terms of where it's maneuvering and where it's going, like Team 1 was implying. And this allows our rover to move much, much faster than the 0.01 miles per hour that current rovers on Mars go. And it allows us to do much, much more research without having to put our crew in danger by moving them further and further and further away from our habitation. And now we're going to talk about our human support and life support systems.
All right, I'll take it from there. So the biggest concerns we had about our human factors were our beacon radius, our passageway design, and things about our crew. So let me just start off with our beacon radius. I just want to clarify that we have 2 ham radio beacons for the new era crew to use. One will be placed in the Hab and one will be placed in the pressurized truck named Achieve. This is also in our report. The beacon's 200-meter radius will also help ensure the safety of the Marsonauts. This allows the crew to have a stationary setup for contact when around 200 meters away from the Hab, as well as have a portable moving beacon. On excursions, the crew will most likely work in pairs. But if, for example, a crew member does not respond to multiple calls over the radio, the astronauts will be able to infer that that colleague is farther away than intended and can accordingly react to ensure the safety of their own crew member. Also, if ham radio communication fails, there's a backup comm system already provided within the spacesuit, so this could be used if the crew intends to stray further apart. We had a question about our passageway design. Let me clarify that not all corridors are just passages. The longer passageway length was put specifically in place to allow more available area for storage space as needed for the astronauts. Some corridors have established airlocks that we've marked in our report and presentation, like between the living module and the laboratory module. In addition, if there's some contamination, the long hallway will mean that contamination reaches the central living or any other module later than if they were connected door to door. So, next slide. Okay, so we had a question about our crew. So the crew age range is going to be 26 to 35-year-olds. The question was, why such young crew members? So physical and muscular strength and capability are scientifically the highest around age 25. Bone strength is also scientifically proven to be the highest around age 30. And you have to understand that the final crew is decided upon established criteria. We're not just taking random 26-year-olds to Mars, if that's the age that arises concern. About having a doctor on the mission, we say that if we do not take a doctor as part of the crew, we might as well not take a psychologist either. Anything can happen to the crew on Mars, and having a doctor is more likely to ensure their health and safety. So although everyone would have basic training in medicine and first aid, obviously, having a designated doctor do the majority of the work and make the calls in the case of health-related issues is going to make it much more convenient and safer for the astronauts. It's going to cause a lot of confusion if there wasn't a field medic or designated doctor, especially in the case of emergencies or difficult situations. So I'm going to hand it back to Vaibhav now to talk about why our engineering is good.
So now that we've responded to all of the questions that we've received, we're going to start talking about why our mission is the best. So like Venkata said, I'm going to start off with the engineering. So firstly, all of our machinery, the truck, the drilling equipment, the rovers, they all include communication devices as well as our balloons that are able to provide us with high levels of efficiency, especially considering our weight limit, especially since we have about 2,000 kilograms of weight to spare on our whole mission, where we can continue to bring more and more scientific equipment as we see necessary as we get closer and closer to the mission date. To support that, I'd like to say that the drilling system that we've come up with and the whole process that we have to create energy for our habitation is completely transportable by our truck and allows us to have significant flexibility on where we place it and what we want our Hab design to be for our mission. So for compatibility's sake with each module, namely the cryogenic gas storage, the methane production system, and the electrolysis centrifuge, the manned rover will be battery powered with a solar panel to increase the battery life and range of the vehicle. The mobile lab, which is another module on the truck, will also have solar panels for the same reason, and an enlarged disk for communication with orbital infrastructure. This will enable long-range communications with the main habitat at the main mission site and connection with the command back to Earth for any last-minute scientific research. In this matter, our engineering systems work together fluidly and are multifunctional and flexible, which means we can easily adjust them according to our surroundings in case of emergencies or difficult situations. Also note that a majority of our equipment can be completely independent from our habitation. So if our astronauts need to go off-site, like I was talking about earlier, to maybe explore something that the rover saw or see an interesting geologic site or have to rescue a crew member, they have the complete ability to do that for months on end if they really need to. So our engineering is the most detailed of all the teams. We take into account from everything like the jagged rocks that our rover will need to traverse to the 11% loss of efficiency our electrolysis chamber will need to endure due to the microgravity on Mars. using spring tires and a centrifuge to combat these problems respectively. We meticulously calculated the exact energy requirements for our habitation and made sure that even in our worst case scenario, we are still overproducing any form of energy that we need, which again is independent from anything we need to bring on Earth, as it's all completely made on Mars through either solar power or methane production. All of our technology is here today in some fashion or another, unlike many of the other teams who may need to design completely new exoskeleton suits, planes, movement machines, and all those things like that. And this makes our mission unique in the sense that if we had the trained crew and the ability to get to Mars, we could set foot on Mars a full decade before any of the other missions right now can, at least from an engineering standpoint. And now we're going to continue by talking about our human factors and life support.
Okay, I'm going to continue this. Our mission is probably the most well-planned in terms of human resources and planning, as well as due to the fact that we've tried to pay attention to the many dimensions that come with being human. Humans going to Mars are going beyond any boundaries any human has ever known. And I think you can see from our report, we've tried to think about the known obvious impacts that will have on their mental health, and which will be an overarching factor as the mission moves on, as well as address those issues by posing probable methods in which the astronauts can deal with these effects while they're on the mission. The selection process and criteria under which the New Era crew is selected automatically indicates the kind of people and explorers that would be required for this mission. And we've also indicated and kept in mind the kind of training that they will need. Our life support systems and things like water, communication, and shelter all have backup systems and have integrated and explained complete cycles to make the most of energy production and resources. Something that adds to the uniqueness of our mission planning is that we've also looked into and written in required detail about our waste disposal systems, as well as what and how certain things can be recycled. This is going to be a huge component when planning such a mission to another planet, especially if we're trying to also bring light to what is happening on Earth. The nutrition plan for our mission also seems to be significantly different and ultimately better compared to the other teams. We've kept in mind menu fatigue and how the diet might affect the mental health of the crew, and accordingly mentioned what should be done so that it complements their physical health. All these seemingly minor things that we've mentioned in detail in our report and presentation are in fact going to be major factors for the real mission, and this clearly shows our thought process while designing the mission, making it more realistic and viable. I'm going to ask Arya to continue with the science.
Thank you, Maya. Okay, so lastly, here's where our science aspect of the mission is the best and why we're able to take advantage of our resources to efficiently get the most scientific exploration done within a fairly short span of time. Now, for the purposes of methane detection in northwestern Utopia Planitia, the ground rover will hold a tunable laser spectrometer, or TLS, with a new feature for gas in scattering media absorption spectroscopy. It's a long name, I know, gas mass. So the TLS measures light absorption at different wavelengths to measure the concentrations of compounds such as methane in the atmosphere of Mars. It has a chamber or a Harriot cell and mirrors when a laser beam passes through the gas sample 81 times, making the measurement and analysis extremely efficient for a 20 centimeter size instrument. Now, for the purposes of searching for life, there are three main instruments in the rover: the sign of life detector, which has two main components to it: the sandwich microarray immunoassay and a competitive microarray immunoassay. So this way, we're able to detect extinct life, molecular biomarkers, and other small molecules, including extinct life system from Earth-like life. We were able to determine the nature and some chemical processes of life if it is said to be found. The detailed analysis will make it easy to study this new system of life without harming the astronauts or their life. Now, additionally, the total weight of the instrument is only 7 kgs. For the purposes of digging into the ground, a large 1 meter long drill with a specialized drill bit will be used to dig into the ground and a pneumatic tube will transfer and save up to 30 pounds worth of samples in storage for the crew to analyze later. Moreover, our drilling instruments allows for the rover to take accurate temperature readings of the subsurface of Mars, which has yet to be done at the time of writing and will give geologists a new understanding of the subsurface world of Mars. Now, as you can see, we're able to make use of significantly smaller equipment and still have major scientific exploration done, including studying the soil, ice, and geological aspects of Mars. One of our biggest objectives is, in fact, to study the atmosphere of the planet as well, and not just whatever is present on or inside the ground. So as to what is within my knowledge, none of the other teams have exclusively talked about studying the atmosphere on Mars, dismissing its benefits to scientific exploration entirely. Now, studying the atmosphere of Mars will be done via balloons. For basic atmospheric measurements, the balloon will feature miscellaneous atmospheric monitors such as temperature and pressure monitors, a sun sensor, and an accelerometer. Moreover, the location of the balloon will be given by a tracking device, which will also provide information on the speed and direction of the winds at any point in time. Moreover, there will be a monitor for the water vapor concentration and the mean size of dust particles in an area to investigate the dynamics of dust and water on Mars. We also have a hypercam methane, which will be mounted to look for traces of methane around the areas where a dust level is occurring or has recently occurred. The hypercam methane is a hyperspectral spectrometer specifically for monitoring methane gas even at low flow rates. Now, from a balloon, it can visualize methane in real time and localize the source and direction of the methane gas. This will provide new data on the mysterious methane distributions on Mars, which by far scientists are still struggling to understand. Conveniently, the instrument can withstand changing weather conditions of the planet's harsh outdoors, making the hypercam handy for dust level studies. Now, we also plan to study rare lightning occurrences on the planet. Our landing site is specifically chosen, so we have the most optimal environment to be able to study all of these. Additionally, the balloon will also carry a microwave detector that is capable of finding signs of electrical discharges in the Martian atmosphere. Due to the increased friction of dust particles within dust levels, they are the perfect site to detect rare lightning events on Mars and understand their role in methane production. Now, in this way, I conclude by saying that the New Era team lives up to its name, being able to cover the most of scientific exploration alongside having designed efficient systems pertaining to engineering as well as life support and human factor systems. We have the best mission to guide humanity to a new era of societal and scientific development. We make our case. Thank you.
Yeah, so from what Vibhav, Maya, and Oya said, we will strongly believe that the New Era mission has the best mission because it's also by far the most cohesive of all the reports. As another example, we have made logical choices from the beginning all the way to the end, and the landing site directly ties into what we want to take advantage of, which is abundant ice, intriguing geology, and proximity to methane concentrated land. So in addition, we can also justify our choice to stay in a relatively high latitude. We're supporting our crew with a robust thermal control system that will efficiently heat the interior of the habitat using the heat released from our reactors, while still having radiators to eject any excessive heat to the greenhouse or simply the outside. So just in this one example, there is already an exceptional synergy among our science, engineering, and human factors objectives. And this sense that all our individual components come together in a unified harmony is fundamentally what propels the New Era mission at the forefront of this set of 5 impressive mission reports. So I want to leave you with a takeaway that the New Era mission stands for this synergy. And let us not forget, this synergy is symbolized in the very name of our mission, which means nourish, endure, wonder, explore, reach, and achieve. So these words not only embody the qualities that a manned Mars mission would need, but it also signifies the values and drive that humanity as a whole would be able to reignite in a new era of space exploration. And thank you very much. It has been a pleasure to share and discuss our ideas with you. And this is Team New Era signing off for now.
Okay, thank you. Any questions from the judges?
Yeah, I'd like to ask them a question, and if I might, if Team 1 is still around, I do have a question for them. Okay, to Team 2, you said that the solar panels were only a backup power source, that your main power was coming from the fuel cells.
Is that correct? And if so, where is the fuel and oxygen for the fuel cells coming from?
So I can answer that question. So our solar panels are our secondary power source for our habitation and all those types of things where our crew's mainly living, not for our further exploration stuff, but for the oxygen production and all those things, we're going to be mining ice on Mars and using all of those to directly gather all the resources we need. By mining this ice on Mars, doing evaporation to remove all the contaminants through a water filter, we're going to be then putting it into an electrolysis chamber where we can produce oxygen and hydrogen at very high production rates. From there, we're going to be using the Sabatier process and use the CO2 already present in the atmosphere of Mars and the oxygen and hydrogen that we just produced to create methane on Mars, along with another access of oxygen to not only combust the methane, but also for the astronauts to breathe as needed. And then finally, we're going to be using that combustion chamber to heat the Hab through the extra steam produced by the process, and also to directly provide energy for lighting systems and all those other things.
Yeah, but the question is, the electrolysis requires power.
Right.
And where does that power come from?
So the electrolysis chamber on top of it has variety of solar panel arrays on top of it that will provide sufficient enough power for it to do its centrifuge process and do the process of electrolysis.
Okay. All right. So then is team one still around? I see Tobias's iPad. I think.
Leonard, are you here?
I'm here.
Leonard
Yeah.
Cook. I have a question for you. In your report, you said that you could generate 5 kilowatts per kilogram of solar panels. And then on the basis of that estimate, you prescribed 500 kilowatts of power for your base. Where did you get 5 kilowatts per kilogram of solar panels?
Well, my teammate Anthony has researched that. So if he would be here, or if his internet is fixed, he could answer that.
I don't see him right now, Leonard. Maybe we can address this over email. Robert?
All right, thanks. All right, let's move on then.
Yep. Next team is team 3. Are you guys ready to present?
I believe we are. Let me just share my screen.
Okay.
So, Polemos 1 is a mission that is creating the foundation for humanity's future, and today is our last chance to prove it. So, what we haven't done so far is explain to you guys what Polemos actually is. Crewed NASA missions, they're often named after figures from Greek mythology. We've got Mercury, Gemini, Apollo, and now Artemis, which is the Apollo reboot, basically. Ares, the Greek god of war and courage, is the most obvious name for Mars program, since Mars is the Roman god of war, but that's too common. So we did a little digging for other deities that embodied war and were related to Ares, and we came up with Polemos, which is the divine personification of war. And in Greek mythology, the robot Alala, who is the subject of the Athlete Operational Shakedown program, is named after his daughter. And Alala is the divine personification of the Greek war cry.
So just to clarify with the kilopower reactors, the mission will have 2 kilopower reactors, which produce both 10 kilowatts each. The base requires 20 kilowatts of power to function, so 2 reactors is enough. The kilopower reactors are extremely safe as they have passive cooling, a self-regulating design geometry that creates a negative temperature reactivity, and are placed far away from the Hab. NASA estimates that the Habitat Demonstration Unit, HDU, will require 20 kilowatts of power, and our design is based around the HDU with a few small modifications. Team 1 are planning to use solar panels, which only run at 20 to 30% efficiency, meaning space, cost, and weight. or wasted. Team 6 is planning on using a 50 kilowatt kilopower reactor, something that is almost guaranteed to not be developed by the early 2030s. The lander will be used as a temporary habitat for a few days during the assembly and testing of the main habitat. Again, this is an extremely temporary habitat that will be only used for the first few days. This temporary habitat could also be used if there's an issue with the main habitat, but this is unlikely to occur. The habitat will have an exercise area, but specific details were excluded from the paper, as with all the other teams. The habitat will have radiation protection through the use of an H2O tank at the top of the Hab. Team 2 wants to 3D print their habitat on Mars, a technology that is unrealistic for use on the first or on one of the first missions to Mars. They mentioned that, I believe it was Virgin Galactic, were printing parts for their space plane, but that was on Earth, not on a different planet. We have basically no evidence to support this. The only thing we have is being a 3D printer sent to the ISS, but again, that's not on another planet.
So there were a couple criticisms and a couple misconceptions about the Redwater water drilling system. Redwater isn't part of the rover. It's a separate component that will have pipes and cables to both a kilopower reactor and the tank on the Hab. And unlike some of the other concepts for water extraction that we've seen, it doesn't use a tank on the rover to transfer water between the extraction unit and the Hab. The Honeybee Robotics team, who designs, builds, and studies this Redwater program, only encountered one freeze-in during the testing outlined in their paper about it. And this was because they didn't have all of the drill system heated, only about the last third of it. We could easily just place small heaters along the rest of the body for only a tiny increase in power draw. And when this happened during the test, they simply kept the auger going, and after a short period of time, it freed itself. Humans are useful here. We can bring air blasters, we can bring ice picks, and if absolutely necessary, we can probably just brute force it out or in. And in their closed environment, which was a TVAC thermal vacuum chamber, they didn't have that luxury.
Another thing we wanted to clarify was the food provided for the astronauts. Along with the vast variety of produce produced by our hydroponic system, Martian astronauts will also have access to pre-packaged food options brought on the spacecraft. These will include natural form foods, intermediate moisture foods, condiments, as well as rehydratable foods and drinks. These options will assist in combating menu fatigue and reduce weight aboard the spacecraft by containing minimal water.
Some people were wondering, why are the spacesuits lighter than the actual Z-series model? And for our Polymus 1 mission, we'll be using a modified version, not the actual version of the Z-series spacesuits, that features a custom lightweight life support system utilizing the OPS, or the oxygen purge system, which reduces a large portion of the suit's weight. The OPS will contain immediate oxygen in case of an emergency, and our crew will be trained in case of a medical emergency.
Maximus?
All our suits in the rover will be pressurized to 14.69 psi, with the same atmospheric composition, 20% oxygen and 80% nitrogen. Astronauts won't need to breathe oxygen before an EVA like they do on the ISS. The crew will only experience a change in pressure if the EVA suit or the pressure vessel they're in is seriously damaged. In that case, they will evacuate to something that still holds pressure and make repairs. Polymus 1 doesn't need an atmospheric processor as big as the one outlined in the source we use. Design in the source could separate 30,000 tons per year, which is way more than our astronauts need, since air will be recycled in the CO2 filtered out and converted into oxygen.
So what we outlined in our original presentation in our design report was that we wanted to keep things ambiguous. We wanted to see what skill set our applicant pool had before we made decisions. And we could tell that a lot of people didn't like that. So in our notes beforehand, we did have a sample of the breakdown of crew specialties. So you can see that everybody has at least 2 or 3 different specialties that they're cross-trained in. And everybody is going to have medical training or at least a knowledge of how to look it up on the database. And here you can see that everybody's fields are in parentheses and everybody's main objective is in italics. Dr. Zubrin actually said himself, through the wise words of Roald Amundsen, that doctors are bad for crew morale, and an experienced explorer should have the ability to take care of any problems anyway. So we decided not to include a designated doctor. We have that scientist who's a medical specialist, but that just means they're a little bit more adept than others. And this is, again, to up the morale.
We're already going to be filtering out polyelectrolytes thanks to ALF. Subsurface radar reflections indicate the presence of debris-covered glaciers as well as buried regional ice sheets in the Utopia and Archaeology Peninsula regions that are up to 170 meters thick and nearly pure ice. We expect to find ice about as pure as that found by Phoenix.
Sebastian?
Yep, just needed to unmute there. We got some criticism of our landing site in Milankovic crater, really just because it's a crater, but it's 118 kilometers wide, so it's pretty big as craters go. I would say, in response to the criticism that our rover might not be able to make it out of the crater, every mission is going to be restricted in the area it can explore by geological features and or the range of their rovers. So no single human mission will be able to explore all of Mars, especially within 550 days. The 11,000 square kilometers of land on the crater floor is actually quite a lot. To put that in perspective, that's slightly smaller than the land area of Connecticut. And additionally, the wide range of features within Milankovic gives us a good summary of Martian geology. The lava flows, subsurface ice, flat plains, aeolian deposits, the central peak, and a smaller crater. Well, it's hard to find such a variety of features in one area that can be explored by one mission. We think that makes our landing site very scientifically valuable. And while NASA has never chosen Milankovic as a landing site for a rover, that is pretty much the same reason they chose Jezero crater as the landing site for Perseverance. Lots of different stuff, all close together. Additionally, we think there will always be later missions to Mars, and especially to Milankovic, because it's such a promising source for subsurface ice, and colonies will really need that. However, future missions aren't required to occur for Polemos 1 to be a success, in our opinion, but they can reuse our equipment and retrieve some of our samples if they do come to the same area, which helps make the investment in Polemos 1 even more worth it. Finally, there's no benefit to leaving the area around the habitat for good if it fails, because the rover can only sustain a crew of 2 for 2 weeks. It can't be used as a long-term replacement, but this is similar to other designs in this contest, so we don't really think of it as a huge limitation. Because we're designing the first crewed mission to Mars, there won't really be helpful infrastructure anywhere else on the planet, so there's no reason to try to leave the crater to get spare parts. despite what For All Mankind teaches. We expect the engineers on our crew will fix whatever problems arise using their own knowledge, technical manuals for the affected components, and advice sent for mission control on Earth. One last thing on the landing sites. Sorry to surprise you, Peyton. I remember someone mentioned something about the, I guess I would say habitability, but general climate of Milankovitch, and the fact that nothing has landed in the crater before, so maybe there is something unknown. We don't think Milankovitch is going to be any different than the rest of the surface of Mars, which is already a planet that's completely new to the humans we're sending.
Why Palaemos 1? Mars is there, waiting to reach. Buzz Aldrin. Palaemos 1 is about humanity's future. The mission will land in the ice-laden scarps of Milankovitch crater, a site that was historically home to lava flows. The mission will take a deep dive into the geology, possible biology, atmospheric composition, regolith, and water of Mars. All of this will be important as we begin the colonization of Mars and make one big step for mankind. Palaemos 1 is our future. Together we can make it real. And then I quickly want to share screen here.
Yeah, let me just stop sharing for you. I actually don't know how to stop sharing. Oh, there we go.
Yeah, I think you already stopped.
So I put in the mission to Mars server. Here, I'm gonna mute this just quickly. But I made this interactive demo here in Unreal Engine. So if the judges want to check this out as well, it's available for Windows. There's also a video. I'm not going to play the whole thing here, but there's also that. And of course, Palaemos 1 is great for merchandising, like in Spaceballs. Thank you.
Thank you, Team 3. Judges, any questions?
I have a question. Could you clarify? I was a little confused by something. How do you get the water from the ice to the system in the Hab that is processing it? Go through that step by step. The water's in the ice, and then how is it extracted and transported to whatever vessel in your habitat system that is then processing it further? I don't have the diagram on me right now, but Redwater has a system where it cycles hot water. Originally, it will be from the water that is carved out and melted by the auger. There's a sealing ring that will expand to fill the bore completely and prevent sublimation. And then it's just a matter of melting the ice, extracting that water, and the cycle keeps going on and on. So some of this water that is already being delivered by a tube through the kilopower reactors radiators, some of that water is also going to be hooked up to a line that will go to the Hab. And so this Hab will contain the ALF, and it'll be run through that first before being put into the large storage tank up top. So, okay, you've explained how you get the water out of the ice and into liquid form and up to the surface. Now, when it's at the surface, are you transporting it all the way to the Hab by a pipeline, or do you have a tank on a truck that you are moving it back? How are you moving the water? It'll be a pipeline, yes. That'll be one of the things that is assembled and hooked into the required systems during our 30-day setup period. So where do you envision getting the water from? From the immediate vicinity of the Hab or from some distance? And I think Maximus has a better idea than I have about where those reactors will be placed to ensure good spacing from the Hab, but those will be run along with the power cables. So if we're running a power cable back to the Hab, we should be able to run a pipeline back to the Hab.
Sebastian, I saw you had a comment there too. Did you want to add something to that?
Yeah, as the person who drew the little red X on the map of Milankovic and did a lot of the research for the landing site, we chose the precise coordinates of our site so that we could land the Hab as close as possible to the scarps, and then mentioned that we plan on not hitting the scarps because we expect the lander for the Hab to use terrain relative navigation, like Perseverance. Anyway, point is the pipeline doesn't have to be 10 kilometers long. It should be far shorter than that.
Any other questions? Okay. Team 5, you're now on deck. Thank you, Team 3.
Thank you, Team 3.
Team 5, are you ready to present?
Yes.
All right, can you see my screen?
Yes.
Okay.
Okay, so to start off with some general criticisms and questions, we had some questions about using methane as rocket fuel. So we're only using the Sabatier process as a part of our recycling system to create additional water. We're only using methane mentioned by the Sabatier reactor as a way for future missions to produce ISRU fuel. So in this mission, the MAV is assumed to be already fueled. For 3D printing, we have brought our own printing material, and the 3D printer itself only has dimensions to create small parts or pieces that will be assembled together later on and be implemented. The 4-seater rover, we had some questions on the power source for that. So the developments in Stirling generator technology and using multiple units can provide the power necessary to power the manned 4-seat vehicle. And 40 miles per hour is the maximum speed the rover can achieve, but it is not the speed it will be usually traveling at. Mars mission designs have anticipated Stirling radioisotope generators to produce as much as 5 kilowatts or 5 kWe. So we have a link for that as well. Our aeroponic systems were chosen primarily because it doesn't require a lot of water as compared to hydroponics. And since the water is being sprayed onto the roots of the plants, the harvests aren't very easily ruined and disease will not spread easily. It also speeds up plant growth, which would likely leave extra imported processed food left over to be used at a later date in case of an emergency. And I think it's also important to mention that our 2 aeroponic towers will be functioning independently from one another. And so it's unlikely that a bad harvest in one tower will lead to a bad harvest in another. And for radiation protection, we'll be using HDPE, Kevlar, BNNTs, which are boron nitride nanotubes, anti-radiation medicine and supplements. Emergency shelter and procedures about what to do in a threatening SPE event are listed in our report. So some people were confused of why we chose human effects for our main objective when there are other possible scientific research to do. And so one of the reasons that we chose this is to see if Mars was viable for a long-term colony, as well as to see how our astronauts will respond while on a distant celestial object for long periods of time. And we feel that it's important to understand how long-term space exploration affects both people's physical and mental health. And some people wanted to know if weather balloons could be deployed by unmanned missions. And
Logistically, for a rover to unfold, inflate, and properly deploy a balloon, it would require extremely complicated engineering compared to a human doing the task. Humans deploying these balloons would also allow for real-time tracking and observation of weather using the tools that will be attached to the balloons. And for drilling, we believe that a 10-meter depth is sufficient because most subsurface ice at Utopia Planitia would be available at around that depth. It's also possible to 3D print a small extension to attach to the mechanical drill in case it isn't quite enough. And we'll be using ground penetrating radar in order to locate the subsurface ice deposits that we will be gathering water from. We will be using a hot water drill to melt the ice initially, which runs on liquid fuel, but can be adapted for a nuclear reactor. The heater in the rod well will prevent the water from freezing again while it's being gathered, and the pump for the rod well is both insulated and relatively short, which will also help to prevent refreezing. And this strategy is already very established in the polar regions of Earth for ice mining. And so the SHARAD on the Mars Reconnaissance Orbiter has detected dozens of large subsurface ice deposits that are 50 to 85% water ice by volume. And we have a couple of links as well for this. And so one team asked who will do the research to find geological traces of life if we don't have a specialized geologist. And as our primary mission objective is to study the Martian conditions effects on humans, the research can only be done by a human on Mars. We do not plan on finding traces of life or current life within our rock samples. We do, however, plan to search for life inside of Martian ice and water. And any experiments regarding possible life on Mars will be conducted by our astrobiologist. Further analysis of possibly interesting geological samples can be done on Earth. And if somebody gets sick, all of our crew is first aid trained in order to ensure that everybody stays healthy and safe. There's a medical bay within our Hab to quarantine sick crew, and any serious injuries can be discussed via telemedical calls in order to come up with a plan for how to help them. And we don't have a specialist to conduct any of our health screenings because all astronauts will be expected to monitor themselves psychologically through a journal and basically just little tests to describe their own mental health. And our astronauts would also be trained to conduct physical health screening on each other as a part of their first aid training. Medical evaluations can be done through telemedicine, as our mission objectives include monitoring humans' vitals and illnesses, and injuries will be closely watched by experts on Earth. None of our measurements require surgery. So the Hab weight includes the fabric needed to adequately shield Marsnauts from not only radiation, but also outside environmental conditions, which include insulation for temperature, air pressure, and possible debris impacts, and to prevent air and water from escaping the Hab. We also included 800 pounds, not 800 kilograms of exercise equipment, which is important to prevent bone and muscle density loss, especially as they're spending 355 Martian sols, along with about 7 months of travel to and from Earth. As one of our main mission objectives is studying human data from exercise, or studying human effects, data from exercise would be important to collect. As the Hab is quite compact, the astronauts will not have much physical movement within it, but can get some form of exercise from conducting EVAs as well. More research has been done in reducing the weight and size of scientific equipment rather than the weight and size of exercise equipment, which is why it has such a high weight. And the weight spreadsheet and cost, there seemed to be some confusion regarding our team's weight spreadsheet because we did it in pounds instead of kilograms to make it easier for us, as we're all from America, the United States, but we decided to include kilogram measurements in our spreadsheet as well to kind of reduce any confusion that might have taken place from that. And along with our weight reduction techniques, several cost reduction techniques were also employed in our mission. Some examples of these techniques are in situ resource utilization
and using an inflatable structure for a HAB instead of a solid metal structure, as well as 3D printing spare parts instead of bringing them to Mars from Earth.
A couple of questions we had about our life support, which I'll be covering for today, is decompression sickness. So at all times, we keep an Earth-like pressure in the HAB, in the rovers, and our IVA suits utilize our adjustable mechanical counter pressure suits, which can adjust to the pressure of, regardless of like the pressure of the outside world. So if you're transitioning from going from a pressurized rover to an outside space, you can tighten the suit to maintain that same pressure. For menu fatigue, we plan to grow a variety of crops using our crew's stay on Mars. The astronauts can change the menu seasonally, as well as add different spices or seasonings to their food to provide different flavors. Any nutrients that are not gathered from this food will come in the form of supplements. And our life support backpack. Our life support backpack will include both a primary and emergency oxygen tank, as well as a water supply to drink, a vital monitoring device, which measures body temperatures, pulse rate, respiration rate, blood pressure, and also has a waste management system to collect urine, sweat, and solid waste. Going further into our waste management system for the HAB, the ECLSS will collect water, and remaining solid waste will be stored in the Martian ascent vehicle to be brought back to Earth. This will also prevent any biological contamination of Mars by Earth microbes. For communication, our crew will communicate between themselves, as in the HAB vehicle and the spacesuits, and to a satellite for Earth if the LCRD optical payload fails. We'll be using a radio wave system for that, and the HAB will mainly use an optical laser communication system to talk with Earth, mainly for high data messages, such as sending maps or just sample data as well. For exercise, a portion of the day is dedicated to exercise using 3 equipments: the treadmill, bicycle, and weightlift, based on the International Space Station's ARIDS device, and the use of neuroelectrical muscular stimulation. So in the case that a crew member is too tired to exercise or is somehow injured in a way that they cannot exercise, neuroelectrical muscular stimulation will be able to exercise their muscles. It's also used in bedridden patients to make sure that they don't get muscle atrophy. So this method is already well established. For our extra spacesuit, we do include a spare suit in our mission payload weight. For suit design, I think I already covered this before, but we have a IVA mechanical counter pressure suit. Then our EVA suit will be worn on top of that. We also have an EVA prep room in our habitat, which will give all the materials needed to properly put on and take off the suit. And our drone, I think we got a question about whether it was realistic that our drone was be capable of drilling. So we'll first like to emphasize that the Ingenuity helicopter has already proved that flight is possible, and NASA is in development of a drone that has a miniature drill as well. Dronecraft will be important to the crew as it will provide visual data from above. It can monitor EVAs, and it can also collect samples from unreachable locations, which are places such as high hills or like dangerous bridges or craters that somehow it'll be too dangerous for the astronauts themselves or their vehicles to travel down to. We also had some questions about our solar Montgolfier weather balloons. The Montgolfier weather balloons will be inflated with hydrogen collected from the Sabatier reactor, and it'll also release bursts of hydrogen to avoid potential obstacles, which won't be much of an issue, as considering the height that it will fly at, it won't crash into like any solid obstacles. This type of balloon design is already well documented and established, and the weight of the balloon and the weight of the instruments kept on is also, is also established in our report. For trash on Mars, I think Team 2 was the one to say this. We completely agree with that. We should not pollute Mars, and that's why the drop sonde weighs less than a pound, and it's also the only planned debris that's going to be left on Mars. And we have to assume that with every mission that we bring to Mars, that there's always some sort of debris that's going to be left behind, and honestly, the only way to keep Mars clean would be to not be there at all. But any debris that's scattered over Mars can be collected and recycled by future missions as well. And a clarification about our ability to soft land instruments using this weather balloon is that we'll be using this specific idea for future missions to deliver instruments and rovers to other or perhaps future settlement locations and to locations that humans cannot reach themselves to deploy these devices. So we'll all make our absolute best to make sure that no trash is left on Mars besides the drop zones themselves, which are quite tiny, so it won't really affect any mission that's going to try to land in that location. For a duration of our mission, we also accounted for, even though we knew that we could stay up for 1.5 years, we had to account for the fact for the mental and physical effects of space on humans. The length of this mission, adding transportation to and from Earth, will be almost around 2 years, and that will be the longest anyone's ever spent in space. Currently, the record is around 437 days, and that was on the ISS, where someone could get more immediate help than rather if they were in deep interplanetary space or on Mars. So, and we chose 1 year because we also wanted, not only we wanted to conduct as much science as possible, we wanted our crew to be able to recover from space travel after the mission. So we don't know how long 2 years would affect them, and considering that they'll be far, far away from Earth. So we also have to conclude that this is only the first mission that's going to lay the groundwork for future missions to improve on, where the data that we find in our mission will be used to find the ways we can increase the amount of times humans can comfortably spend in space and also make EVAs more safer. The more time that you spend on Mars or the more EVAs you take, the higher the risk is. So we should go to Mars, but we also have to understand that the more time you spend there, the more probability that something could happen. For our buggy, we have to again note that 55 miles per hour is the maximum speed of our vehicle, and it's not the speed that it will travel at. Utopia Planitia is also relatively flat, and topographic maps will warn Marsnauts about dangerous terrain ahead in the case that they'll crash into an obstacle. The buggy itself is also designed to protect its passengers in the case it flips over. And for navigating smaller obstacles, we utilize knit-to-know mesh spring tires that can mold around these small obstacles. Where in the case if we use inflated or pressurized tires, it might damage the tires. And for a clarification would be that this buggy is only meant for short distance trips, as well as to transport materials from the Hab lander and MAV. So the small radius that it will be used in generally will be already well-known terrain. For the buggy battery, I think we had a question about the rechargeable battery our buggy will use. It uses a rechargeable lithium ion battery that will be charged by the Hab, which the Hab is in turn has its power from the crusty reactor, which will be kept far away from the Hab in order to reduce the likelihood of a nuclear threat. And our aeroponic system maintenance, what technical knowledge that all crew members have, and are all system operations, and the aeroponic system's vertical growth towers is relatively easy to assemble and to maintain, especially with the crew's botanist expertise. Although aeroponics does require a constant source of power, the two crusty reactors that are in this mission are capable of producing a constant power source, and it's highly unlikely that both of them will somehow fail at the exact same time. The benefits of having an aeroponic system also outweigh the costs, as that's a 30% higher crop yield and grows 3 times more quickly than crops in soil. And I provided 2 references for that claim. For the habitat and greenhouses material, the inflatable habitat is mostly fabric-based in order to prevent secondary radiation. And most of the layers do contribute to radiation shielding along with protection from outside weather conditions. Some of these materials off the top of my head could be mylar, urethane, which prevents water or from escaping the Hab. For our laser someone had a question about laser communications light diffusion. Optical laser communications from orbit to Earth is already well established, And considering that the Martian atmosphere is over 100 times thinner than Earth, light diffusion won't pose much of a problem. Our last question was on the 4-seater pressurized rover materials. So the rover's outside frame is made from aluminum alloys, which is already used on other missions for Mars, and also utilizes the same shielding fabrics as the Hab and the spacesuit. Why our mission? Our mission strikes a realistic balance between doing as much science as possible, as well as keeping the crew safe. We are following a historical pattern of exploring new frontiers. So the first missions to a place like the moon or space is either unmanned or just to prove that a human presence is feasible. Subsequent missions after this are based on a knowledge and data that are able to expand the mission duration and the number of EVAs taken. For an example, we have the Skylab and the ISS. The Skylab was a temporary environment while the ISS was used for much longer than that. And based on the results of the Skylab, the ISS was built. For the Artemis mission and the Lunar Gateway, the first series of Artemis missions are going to be unmanned missions before we have our lunar landing with humans on it. And in the future, the Artemis missions will be the stepping stone for Lunar Gateway station. And the same pattern is following for the Mars exploration plans. We first had unmanned vehicles on Mars. Then we're going to have our mission that's going to establish a human presence and prove that it's feasible. And subsequent missions will expand on top of that and stay on Mars longer and even make a permanent settlement. We also have to account for the fact that even though the longer we stay on Mars, the more likely it's going to fail. So if this mission fails, funding and public interest in manned space explorations will decrease. Society will be very hesitant, even with better technology in the future, to have another Mars mission if the first is not successful. For example, we're still hesitant to search for life after the Viking incident. Even after finding a meteorite, we are still hesitant to look for life on Mars. This crew and mission will provide the data and knowledge that future missions will be using to build upon for their mission plan design and improve upon the technologies that we'll use in our mission. The technology used on this mission will also find its uses here on Earth, especially through telemedicine, help doctors reach patients in remote locations, to the mass use of optical laser communications and aeroponics.
And so our mission conducts a variety of experiments that will provide data on gathering resources for a human settlement, as well as keeping the humans alive and healthy. Our mission can prove the viability of future Mars missions and colonization by studying how humans react both mentally and physically to the Martian environment, which is something that not a lot of the other teams have considered. We are the only team that focused primarily on the comfort, health, and safety of our astronauts. We included both leisurely activities for the astronauts to participate in during their free time, as well as exercise equipment to maintain peak physical fitness and health. And we are the only mission that went in depth about decontamination procedures to preserve Mars and protect the crew and Earth.
At last, we'd like to say thank you to the Mars Society and for the other teams for giving us this criticism and providing us the opportunity to look back at our mission plan. And I want to say thank you to our mentor as well. And that'll be all, I believe.
Okay, thank you, Team 5. Judges, any questions for Team 5?
I just want to clarify something. Maybe I'm confused about this. In one place, you said your rover was powered by a Stirling reactor, and another place you said it was powered by batteries, charged up by your crusty reactor. Which is it?
Oh, so we have two vehicles. We have a 4-seater pressurized vehicle, and we have a 2-seater buggy that's unpressurized.
And so which is powered by which?
So the buggy uses a rechargeable battery, while the 4-seater pressurized vehicle uses the Stirling.
4-seater pressure uses the Stirling, which is powered at 5 kilowatts.
Is that correct? And then the buggy uses batteries.
Yes, it uses batteries that are recharged using the Hab, which is in turn gets its power from the cluster reactors.
Got it. Thank you.
Gary, do you have a question?
Yeah, this question is for Sean. I like very much, first of all, the entire presentation, but one of the things that you brought up is something about anti-radiation protection. And I know that none of the other groups have brought this up. When you say anti-radiation, you said anti-radiation medications will be given. Do you have any idea of what those medications would be? And how do you actually give a medication for radiation sickness? Do you know anything about that? Is that why you entered that?
So Shreya did a lot of research on radiation protection, and so I believe she has the link to that, but it's basically a medicine that you can take after exposure to relatively high doses of radiation to minimize the effects on the human body.
Gamma radiation specifically, and other radiation caused from nuclear weapons and such.
All right, thank you. That's an interesting area. Thank you.
I just have also one other question. You're using aeroponics. Is the entire diet of the crew produced by your aeroponics, or do you have other foods as well?
So a vast majority will be produced by aeroponic crops, but we are also bringing some processed foods from Earth, and we think that there will be food left over from the initial supply that we bring to be implemented into the astronauts' diets later on.
Okay, thanks.
Any other questions? Okay, thank you, Team 5. Good job. Our last team is Team 6. Are you guys ready?
Yes, sir, we are. Can you hear me?
Yes, go ahead.
Okay, so the first thing, I'm going to go about this through most of the, like, which teams did what. So first thing with Team 2, one of the things for their general topics was the radiation. And we had considered that there was more extreme radiation on Mars, but that, like, we did consider it, and that's why we had more radiation materials in our Hab. So we had some water for basic, and then it was made out of Kevlar mainly, and which is a bit more, and then mainly, I believe, bismuth infused panels, and that was we believed that was enough. For our water filtration, which I believe there was something about, we had included that in our water production part of the report. We had at least enough to get us through. For menu fatigue, that was something that we had definitely considered, because we're going to be mainly eating potatoes. So our main counter for the menu fatigue was the algae that we're growing, as well as the seaweed. And every now and then they will be able to eat algae and seaweed just as something extra, something green. The rover, I believe, so our rover, it's unpressurized, and the main purpose is not to get the crew to faraway places. Instead, it's mainly for transporting cargo, and since it's unpressurized, the crew will have their suits on in the rover while they're transporting materials. So for another thing from Team 2 was a lot about our algae. I believe somebody had said that was our main, they believed that was one of our main focus areas. I believe that was a bit of a misconception because it's more of a bonus. We are going to be researching it, but it's not our
major focus. It's also not our main nutrition, like I said a minute ago. It's just a bit of a extra thing for the crew to eat. And the last thing that Team 2 had talked about was for us was the exercise. So we are planning to bring exercise equipment. We'll have weights and just general equipment. So we don't have a specific exercise schedule, but our doctor can definitely help recommend or just help out with the exercise and make sure everybody is doing it. For Team 5, one of their questions was the archaeologist or archaeology, which is one of our focuses for our mission, and who had the skills. So our geologist is the one with they do have training in the archaeology. I believe we had that on our report, but not our presentation, and I apologize for that. So you also asked about if ice water was if it was in scattered pockets around the Niger Vallis or just generally spread out. I believe it's generally spread out, and we would be transferring multiple ice cores at a time in the rover. And then the last thing I believe was about our algae again. So somebody had said that we are how we plan to modify it. I don't believe we are modifying it. That may have been something that if one of my teammates wants to pitch on that, but I don't believe we are modifying it. And I think that's all for Team 5. And then Team 3, one of the things was, and this has been discussed multiple times from other teams, is the doctor. So I think it's good points about why you don't need a doctor. But so one of the things was it can lower morale because, like, I don't know, I guess some doctors can be arrogant and just, I don't know, most people don't like them too much. But I think if something severe happens that to one of the crew, then that can lower the morale a lot more than having the doctor there in general. For the food, we are not growing it. I believe a lot of people believed that we're not growing the food. We've got enough space to bring all of the food that we need. And another misconception, by the way, is we're not staying for the 1.5 years. We've actually decided to stay for 6 months. And so even if we were growing it, I don't believe we would need as much space. But yeah, we're not growing our food. And then the final thing for Team 3 was about our energy, so that was actually a mistake on our part. I believe somewhere whenever we were making or writing up our report and making our design, I'm not sure where, but somewhere some miscommunication had happened. And I think the person that was working on that had seen so we've got a link to the source for the kilopower reactors that we had found and we're mainly looking at. And I believe he saw 50 kilowatts, but he didn't see that we would actually need 5 kilowatt reactors. So 4 and a spare for all of the energy that we would need. That was a misconception that was a mistake on our part. And I believe, something from Team 5 was our nitrogen solution or situation. We are gonna have to bring 2 50-liter tanks, I believe. 2 50-liter tanks of nitrogen. And when we were looking through the critiques, I don't believe Team 1 had said anything, if at least that we could find. So
I believe that's it. And I'm going to pass it on to Nathan, who's going to continue on the presentation. All right, one second. Let me share this slide here. Okay. So this is going to be our reasons of why we believe our mission is actually pretty good. Shoot, I put it in full screen. One second. Okay, so our core benefits of our mission include it being inexpensive, lightweight, and the combined value of both of those leading to potential advantages of several ongoing missions, as well as us using only proven technology for our mission mostly. Next slide. Okay, so our inexpensive. So our mission design is fairly inexpensive compared to other mission designs, but at the same time completes all goals of a standard Mars mission. Our mission achieves the lowest costs using an inflatable habitation module and lightweight materials. We still achieve all scientific goals. We also have have the ability to set it all out with ease. Our system would be excellent scouting missions for the near future. So saying like, this would sort of be like your first step in a location where if you find something interesting, you could send in the future like a more advanced and detailed if you find something that you want to look into further. Next slide, please. Okay, lightweight. So our mission is very lightweight, actually. It's roughly 13 metric tons. The weight of our mission provides lots of room for any adjustment in parameters. This also brings in possibility for collaboration with other international groups, say like ESA or just other foreign programs. Furthermore, our mission is feasible enough to be modified repeatedly and resent out into new locations or in the same location with a different set of goals. So with this amount of extra weight to fit in the limit of the program, we can optionally include specific instruments for different locations should an opportunity arise. All right, multiple simultaneous missions. So along with the other aspects, the possibility for multiple missions being carried out at the same time is also reasonable. The core design of the mission would undergo little to no change in different locations or environments, making it very adaptable and easily performed. So for example, the rover swapping out for a drill or other pieces. So say you want to drill in a different location and you could swap out different parts that would be important in other areas that in this new area you wouldn't really need. So you could bring in more specific things for something that you've already found in previous missions. All right, next slide. All right, so proven technology. So we strived for making our mission as reasonable as possible for modern use. All parts and models of our design are possible in the current time period, making reliance on future variables less detrimental to our mission goal if they ever turn out to not be as applicable as we would think or useful. These would also range from our power supply to our life system. So pointing out the kilopower is definitely feasible. With now this part is a little bit into the future, having enough efficiency, but it is preceded in NASA of having the capability of producing enough power sources for our entire mission. And then I will pass that on to Aaron to finish us off.
Okay, so my team kind of left me hanging here. I don't know what to say other than if anyone has any questions. And we'd like to thank the Mars Society and the mentors, specifically Mr. Kent Nebergall, who helped us significantly with the design of our mission. Again, we thank you for letting us learn with this program.
Any questions for Team 6?
Yeah, got some questions. I just like a clarification because at one point you said you were feeding the crew with potatoes and algae, and at another point you said you were bringing all your own food. Are you bringing potatoes and algae, or are you growing the potatoes and algae?
I can answer that. We're going to be bringing the potatoes. The algae is really more of a side experiment. We will be bringing algae, but we'll also be growing it and optionally eating it if we see need to.
but we are going to be bringing our main food supply with us.
Okay, and so you're bringing potatoes. If you're bringing the food, why bring potatoes as opposed to steaks and nectarines and other stuff like that?
I believe it was, I didn't do too much in this area,
I
but
can
believe,
take this over,
okay,
Nathan.
you can have it.
Okay, so if I'm remembering correctly about the discussion, it was that we have a lot of the general nutrition figured out, and the potatoes was simply for caloric intake, and potatoes being very bland, you can easily add different flavoring to it without compromising the dish. And another reason why we had chosen potatoes is initially in the plan we had planned on growing them, but then we later ditched that plan, but we kept the potatoes because we already had the numbers for that.
Okay, thank you.
Any other questions?
Well, one more. Can you just review quickly the science goals of the mission?
Okay, if any of my team members see something that I'm missing, please feel free to hop in. But the science goals were to do ice coring similar to that done in Antarctica in the modern day. And then another, sorry, my mouth is not working 100% right now, but another one was geological coring, so that we can study the geology of Mars and potentially find within that the history of Hellas Planitia and Niger Vallis. And since we are going to be close to, if not in the outflow channel, we'd be able to go down and get a sample from hundreds, if not thousands of kilometers away that the water or whatever liquid brought to that area. And a few other minor ones were the performance of algae as a life support system and monitoring the crew for any major defects that happen within the microgravity. If I missed anything, team, please jump in.
Hi, I just want to mention something. One of our other major objectives was, since this is an outflow channel and sedimentation would have been a thing that happened here quite a lot, archaeology will actually be one of our primary aspects. So any members of the team that are going to be going out and doing the experiments will be trained in like basic fossil collection. So they will be equipped with certain tools like trowels, shovels, brushes, and all those. Additionally, we will use potassium argon dating in order to find the age of certain fossils. So in this case, we will be looking for things like trace fossils. So those are things like tracks or impression fossils, which are left when an organism stays on the ocean floor and leaves an impression.
I'd also like to mention, somewhat unrelated, but I'd like to specify that we didn't design multiple missions to go at once. It's just the opportunity of having a mission that can be repeated multiple times at the same time. We didn't design that, and that's not what we were going off of, but I'm just saying that that would be something completely doable if for future missions somebody would like to do that.
Okay. Any other questions? Okay, I'm just going to read, there's a couple of things that have popped up in the chat for the benefit of the recording. I'm going to catch everyone up there. So team one was asked by one of our judges, Nicole, do you have a total cost listed in your paper? And they wrote back, no, we have not. We've focused on providing ways to reduce costs. NASA often exceeds its cost assumptions, so we do not think it's right to give meaningless numbers, especially since some of our technologies are only at the developing stage. And then Team 2 had a rebuttal to something that Team 3 said on this call. So Team 2's representative says, earlier Team 3 said that we are 3D printing regolith for the main structure of the Hab. We're only using the regolith for radiation protection. The primary structure is inflatable as stated in our report. Quote, the regolith structure will serve as a layer of protection from cosmic solar radiation, and beneath this there will be an internal inflatable layer carried from Earth in which the crew will live and work. Inflatables are chosen because they are more flexible and compact and they take up a relatively minimal volume when packed, unquote. They just wanted to make this clear if that was not before. Okay. And then Team 1 also provided an answer for Dr. Zuprin's question about solar panels. They provided a link to a research paper, looks like early commercial demonstration of space solar power using ultra lightweight arrays. Are there any final questions for any of the teams before we close this down?
Well, I'd just like to make a statement.
Go ahead, Robert.
Which is, you know, this is a contest and some team's going to come in first and some team's going to come in fifth and so forth. But from my point of view, you're all winners. The level of work in this contest is way beyond high school level. You know, it's really the sort of thing one might expect from a junior level university design class. So you guys are about 4 years above where you should be, or what, not where you should be, where you might be expected to be. And so, you know, this has been really great. And once again, I have to emphasize that, you know, something that we, the Mars Society, are trying to do here is to demonstrate the value of a new kind of pedagogy for teaching science. And, you know, the heavy lifting on this had to be done by you, because if you guys had just goofed off, you would have made this a failure. You know, so you really have delivered, and I want to thank all of you for the work that you've done.
It's been quite a pleasure, and it's gonna be tough to make the call regarding the teams. I think I'm looking at the reports and they're so detailed and very thorough. So thank you for putting the time, and your team, and you know, every team has to clap their team members. It's an international effort, I think, and you've done a magnificent job. So thank you for making it hard for me. That's a good point there. And I'm looking forward to seeing you on Monday. And, you know, I think all the teams here as the finalists are winners, basically. So well done.
I would also like to say, I'm a high school teacher in the United States, and it's a traditional school. And the amount of work and effort you guys put into this just blows my mind. It's just amazing. And it just makes me I'm just looking forward to the future because of students like you who really care and take the time and do the research, and it's important to your future. It just makes me very happy. And just like Ruth said, thank you for making it hard to make a decision on this. You all did a great job.
I think I'd like to have a word too to all of the students. Fantastic job, just amazing. I used to work at the Armed Forces Radiobiology Research Institute, and when I was in the Army, and so you can see how this would be of interest to me. And then more importantly, I worked at the NIH, National Institutes of Health, as a scientific review officer. And it was my job to organize the reviews of grant applications in the area of infectious disease. And so for over 20 years, I sat around a table and listened to other scientists critique other scientists. And let me tell you, you all at the high school level doing the critiquing, you know, just not making, you know, doing the reports and making the presentation then on Monday, but then critiquing your colleagues, your peers, and then being able to rebut that. The way you did that was just
very professional and very well done. You should really give yourself a lot of praise there. At least I'm giving you praise right now. Fantastic job. I look forward to more things like this coming from the Mars Society and Dr. Zubrin. You all have a great day. You really earned everything over the last couple of days. Bye-bye.
All right, well, we'll see you guys on Monday. I think the last thing I would just say is I hope that this is not the end of your Mars journey. The Mars Society is here for you if you wanted to volunteer in some capacity. If you wanted, as you go into university, we have a University Rover Challenge. We will most likely hold this event again next year, although Robert and I need to talk about things like that a bit and what our overall strategy is for education. But we definitely, I think this was a successful experiment. And so thank you all for being part of it, and we'll see you on Monday.
And also one other thing I want to add is that the winning team is going to be invited to present their design at the Mars Society Convention, which is going to be in Arizona, October 20th through 23rd. You can come in person, and you can come, if you can't make it, which might be true for people who live overseas, we'll let you do it by Zoom. But one way or another, you can do it. And actually, all the teams can present, but the one that's going to be featured big time is the winners. So, okay. So we look forward to having your participation, or you could just come to the conference and hang out and watch all the other talks, which is a fun thing to do.
Yeah, we'll be in person. We also will have a virtual way to attend as well. So definitely check that out. Okay. Thanks, everyone.
Good night from my side.
Thank you so much.
Bye from Israel.
Good afternoon
Bye.
from
Great
Colorado.
job, everyone. Thanks so much. Bye. Bye-bye.
Bye.
Thank you so much.
Thank you.